Hello. Hello, mic check. Hello. Hello, mic check. Hello. और कहीं भी कुछ चल रहा है क्या? मीटिंग वगैरह? हेलो, माइक चेक. हेलो. हेलो, माइक चेक. हेलो.
अभी वो भी नहीं आ रहा है ना।
ऑडियो चेक कर लेना।
ऑडियो चेक कर लिए.
आ रहा है यूट्यूब में।
हाँ सही है। रिमोट।
हाँ, रिमोट वगैरह भी सब किया.
मैंने बाद में ओपन किया था जब नहीं आ रहा था। अभी चालू किया है।
हाँ, अभी चालू. अभी बंद कर देते हैं इसको. डिस्चार्ज होगा.
From Professor Sen, who was the former Dean of this institute and presently Emeritus Professor of HBNI. And after the opening remarks, we follow through by 3 talks and a poster session. So I invite Professor Sen to give the opening remarks.
Good morning. Am I audible? Yeah. Okay. A warm welcome to all of you to this special commemorative event marking the 9th death anniversary of Professor P.K. Kao. You see, our founding director and the father of fusion research in India. On behalf of all of us, I would also like to welcome members of Professor Kao's family, Mrs. Saroj Kao, Siddharth, and Pooja, and other family members who may be joining us online. I also welcome all his former colleagues, students, friends, admirers, and everyone participating in this event and maybe watching on YouTube. This annual gathering is not only an occasion to pay tribute to Professor Kao's memory, but an opportunity to celebrate his extraordinary legacy. As we all know, during his long and distinguished career, Professor Kao played many roles. He was a world-class scientist, an institution builder, an inspiring teacher, and an international ambassador for fusion research. He was also the visionary who conceived and built India's plasma physics and fusion program and laid out a remarkable roadmap for its future. Above all, he was an inspiring human being who touched so many of our lives. We feel truly fortunate to have lived in his time and to have known him. For all these achievements, done over one single lifetime. All of these deserve special celebration. But today we are going to celebrate his scientific legacy. As you know, science was his lifetime passion and his mission. That was the primary goal in his life. Everything else was secondary to him. His work was driven by deep curiosity and a rare ability to connect ideas across different fields. As a result, his scientific interests were remarkably broad. His research spanned so many areas, including laser plasma interactions, which was his first love, tokamaks, space and astrophysical plasmas, quark-gluon plasmas, gravitational waves, dusty plasmas, and thermodynamics of plasmas. He even took interest in things like thermodynamics of life and tried to evolve theories of consciousness. So you can see the breadth of his interest and how passionately devoted he was to doing science. One of his greatest qualities was his ability to share his curiosity with his colleagues and students, and igniting in them the same excitement and commitment that he felt himself. Anybody in this audience who has ever worked with him must know what I mean by this. His working style was very transparent and encouraging. He always treated the opposite member, a person with whom he was working, as his equal, whether he was a colleague or a student, and gave full attention to his or her ideas while solving a problem. This is what helped him build up so many collaborations and friendships throughout his life. This approach and the innate goodness of his heart immediately drew people to him and encouraged them to collaborate with them. So over the years, he built an extensive network of scientific collaborations, and many of you are witness to that here. This was done not only within IPR, but across the other institutes in the country and also internationally. So the collective output of this endeavor, which spans over more than 400 papers, constitute a rich body of scientific knowledge and a very valuable heritage. More importantly, I think they inspired generations of researchers to pursue new ideas and initiatives, ensuring that his legacy continues to grow. So this is the legacy that we are here to celebrate today. To help us do so, we are fortunate to have several distinguished speakers from among Professor Kau's former colleagues and students. First, we have Professor Amita Das, who worked very closely with Professor Kau on a wide range of topics, including laser plasma interactions, dusty plasmas, plasma turbulence, EMHD, and many others. During her time at IPR, as I remember, and she was one of the youngest members of the theory group and brought a lot of energy to the activities of that research. I remember she not only imbibed very quickly Professor Kau's ideas, but also took them to a much higher level and also strengthened them by carrying out very detailed numerical simulations. In fact, I remember the setup she had in that room. We had several computers and all the students working there together, learning from each other under her guidance. So in a way, she established a good tradition of high level and excellent numerical simulation work here at IPR. She was also quite interactive, and in her own way, she would argue with Professor Kau about many of his ideas and took them forth a great deal. I think something that Professor Kau himself appreciated a great deal and encouraged her to do that all her life. She was also a key participant in several collaborative initiatives with Professor Kau, including those with the group at TIFR. In fact, we are missing Professor G. Ravindra Kumar today. Today, she continues to advance his legacy through her research and mentoring at IIT Delhi and at other institutes within the country. So we are very happy and delighted to welcome her. Next is Professor Shishir Deshpande, whom you all know. who was a former student of Professor Cow. He began his research career actually studying instabilities and modeling instabilities and nonlinear phenomena at the tokamak edge, which was one of the frontier topics at that time. Later on, he also headed the numerical modeling group and also started a group to design reactors. This was one of the advanced thinking of Professor Cow, because he was already thinking into the future of what would be required for a reactor. So in reactor design and all, he engaged a small group, and Shishir was a very active member and later on led that group. More than that, I think Professor Cow groomed him and gave him a major responsibility of fulfilling his dream of working with ITER. So he led as a project director of ITER India and played a major leadership role in advancing Professor Cow's one of his dream projects. Today, he continues to contribute to the International Fusion Program as a fellow of ITER. So we're very pleased to have him with us today. Then, of course, there's Professor Sudeep Gupta, another one of Professor Cow's former students. In fact, he became involved in Professor Cow's pioneering work on quark gluon plasmas, along with you, and contributed significantly to applying concepts from plasma physics to understand this exotic state of matter. This was remarkable, in which he transferred ideas from one area to another and successfully modeled these phenomena, which are really far removed from the plasma regime. So as a member of the vibrant theory group at IPR, Sudeep continues to investigate fundamental aspects of nonlinear plasma behavior. His forte is very precise and sophisticated mathematical tools, which he employs very effectively to analyze very complex but very fundamental problems in nonlinear plasma phenomena. Like his mentor, he has a unique teaching style. You will get glimpses of it in his talk, very clear and starting from fundamentals. Like his mentor, he's also built strong international collaboration and trained many talented students. So in all their talks, you will get a flavor of some of the areas that Professor Cow started in this institute and in this country, and how these things have advanced over the years. Finally, during the poster session, the current research scholars of IPR, many of whom are students of Professor Cow's former colleagues and former students, they will present their research. Their work will offer a glimpse of how Professor Cow's scientific legacy continues to inspire and shape new generations of researchers. So we have an exciting day ahead of us, a true celebration of science and of Professor Cow's enduring legacy. So let us make the most of this opportunity to remember, reflect, and to celebrate. Thank you. Yeah.
Prepared a small video compilation remembrance pipeline to the cow. There's nothing to say. I will just show the video. So that has been created.
दो क्लिप हेलो हेलो Thank you, Professor Sen, for a nice introduction. I'd like to. Okay.
Turn up the volume.
I'd like to thank the new director of IPR, Sudeep, Sarvesh, enthusiastic students, and other organizers who conceived this idea of having a meeting in memory of Professor Kao and inviting me on this occasion. It's really going down the memory lanes because here I have spent 27 years, and this seminar room, although it was a little different, I've heard many talks, and Professor Kao used to choose this seat in which Shishir is sitting right now, and always that location. And when speakers used to speak, I used to wander around, like sometimes maybe you all also do, go to sleep, or like your thoughts go around. So that used to happen. But in between, whenever Professor Kao started asking questions, the talk used to become so clear after he started discussing with the speakers that one became interested in the talk, and that was his quality, that from anything he used to extract the best possible message that was underlying in that talk and make things simpler. So I still remember that seat, and today I'm going to talk about, there's a slight change in the topic. The topic of laser plasma interactions from fundamental to frontiers. Professor Kao has done seminal work in this field, both in the fundamental area as well as the frontiers of applications. And today I'm going to highlight how this area continues to offer opportunities in both at the advancement of frontier physics as well as the fundamental physical processes that are involved. And as we know, it is true, and I would like to highlight this, that the fundamental physics forms the architectural framework on which the edifice of frontier science resides. So my talk will have both the touch of fundamental physics and some of the frontier aspects that I would cover in this talk. I'm sorry, these days I feel a little breathless, so I'm not that loud as I used to be when I was in IPR. So you'll have to bear with me. So I feel that I have had a remarkable career, continuous 27 years of intellectual discussions, scientific mentorship from Professor Kao, which is matched by only a couple of you like Professor Sen, Professor John, Shishir, and Jitesh. So I was very fortunate. I feel privileged about it. And the journey was not merely one of, we have a pointer or something? So the journey was not merely one of research collaboration, but I learned a lot of human values from him. And across many disciplines of plasma science, philosophy, and human values, And recently I shared my experiences and reflections on those days in a journal article which has been published in Asian Journal of Physics. And this is the link that has been provided here. So if you wish, you can have, you can read this article. And this talk is therefore a personal tribute to an excellent scientific mind who shaped generations of plasma physicists in India and beyond. This article, I just want to flash them. And you can go and library, I think Saroj has kept a copy there, so you can have a look at this. The other day I was talking to Sarvesh, and he also mentioned how Professor Kao had an office, a very interesting office setup in which the central room was of the PA, and this side he used to meet the administrative guests, and the other room was dedicated to scientific discussions. So often he had to leave the scientific discussions and go and talk to some or attend some immediate administrative matters. And while we were sitting in the scientific discussion, we used to wander off. But back he used to come, and pinpointedly he used to start discussions from there, and we were taken aback. So that was he, very focused and very dedicated to the scientific pursuits. And it is not that he only did science. He had many more other interests, some of which I will also highlight later in the talk. So my journey in IPR has, I think Professor Sen has summarized it. So today I will talk about my journey beyond IPR, which has also been very significantly influenced by Professor Kao in many ways. And I remember it was in the ICPP conference. This year also we are having the ICPP conference in December in India. That was in 2016, 10 years ago, in Taiwan. And in that conference, Professor Kao had mentioned to me the relevance of investigating laser interaction with magnetized plasma. He had noticed that very strong magnetic fields were being generated in laboratory, and they were of the order of kilotesla, 1.4 kilotesla at that time. Now there are proposals of having megatesla order of magnetic field, which survive up to picosecond time scales. So he noticed that, and he also noticed that there were lasers, long wavelength lasers like CO2 lasers, which could be generated in pulse mode, so you could have enhanced power. And that opened up a very new regime in laser plasma interaction, that of investigating a magnetized plasma in which the gyro frequencies of at least the lighter electron species was higher than the laser frequency. And that uncovers many new regimes. And he had specific interest in having, in capturing the dynamics of electrons by the magnetic field, where the ions remain unmagnetized and the energy from the laser could directly be transferred to ions, because the magnetic fields inherently makes the electrons more massive. That was his idea, and he mentioned it to me. And looks like I started working on this particular regime, and it really opens up a wide range of applications and fundamental understanding that I have been working out for the last, since then. And I will give a glimpse of those areas. Then when Professor Kao used to work with Professor Parikh, Jitesh, Sudeep and all on the exotic field of quark-gluon plasma, I used to get very fascinated by and observe it. Any physicist, I think, gets fascinated with this particular topic. And I think Jitesh noticed it. We had a paper common together on chiral, and we calculated the transport coefficient in that particular paper. So that was one particular work. So this field always excited me, and I used to look in how when they used to discuss barely understanding something. So at IIT Delhi, I got an opportunity to work with Professor V. Ravishankar in this particular area. Subramanya Bhatt and Bhushan Paradkar. Is he coming today? No. Okay, so Bhushan Paradkar and with Subramanya Bhatt and Professor Ravishankar, we have carried out a number of work in this particular area. We have shown that non-abelian gauge fields of Yang-Mills plasma, and we were able to solve a decade-old Wu-Yang ambiguity and show connections with synthetic gauge fields. This is the work which we are writing up at the moment, which show connections to synthetic gauge fields for spintronics and laser-cooled atomic levels. We have already a work on collective effects and streaming instabilities, and we are also planning to carry out some particle in cell simulations with Sudeep. We already are working on fluid simulations, and it's very interesting. The fluid simulations that I use is 30 years old, more than 30. It was discovered, the basic software was developed 30 years ago by, I think, Naval Research in US or something, which is known as LCP-FCT, flux corrected method. They have developed a suite of subroutines. It's a very, it has a lot of freedom, and like you can write your own equations, use the suite of subroutines to construct, solve the problems of your interest. And it served for the software is a very rapidly developing field, but it has served its, for the 30 years I have been using this particular software for a variety of problems. It has predicted a number of nonlinear results, which have been also verified in simulations by Sudeep, wave breaking and all those ideas, instabilities and nonlinear states. Generations of students have worked in it, and it is still being, that particular technology that I was able to implement is even giving me benefits even now, because we have now applied it to the Yang-Mills set of equations. So it's very useful. It has remained relevant for almost 3 decades. So as I mentioned, I've been working lately on laser interaction with magnetized plasma. It started with students whom I was guiding at IPR, specifically the 3 first students, Atul Kumar, Ayushi, and Devshri. And here I'd like to digress and mention, especially thank Dr. Hem Joshi, who, when I left IPR, Ayushi and Devshri had not completed their thesis. They were midway. He graciously took them to took the administrative responsibility of the supervisor, as a supervisor, and really helped me a lot while I provided the scientific guidance. There were no bottlenecks that he posed, and I'd like to publicly acknowledge and thank him in this platform. I had Shrimanta Maiti, who joined me at IIT Delhi, Lakshman Goswami, Rohit Juneja, Dhalia, and Animesh Sharma was RA recently. And we uncovered and worked on many aspects. I don't think this is a complete list, but we were able to show preferential ion heating using lower hybrid excitations, localized and directed heating at a particular place, spatial locations. We also showed a very interesting result on electromagnetic wave transparency, which will be observed when the plasma is highly magnetized. That is, even the magnetic fields are so strong that even the ion species becomes magnetized. Then the plasma doesn't work like a dielectric medium. And it connects very nicely with the Maxwell set of equations. Plasma is a dielectric medium. And if you pass an electromagnetic field, the charged species will have a dynamic response. Yet, the electromagnetic waves, it can be shown, has the property of propagation just like a vacuum. Of course, it has to have certain orientations. And that's an interesting problem for undergraduate students in electrodynamics. I often give them this particular idea. And why does this happen? You will notice that the source term in the Maxwell's equation, which is related to currents, in a strongly magnetized case, that is 0, even though ions and electrons move, we were able to show that they move together. So there's no current. And since the current is absent, the electromagnetic wave propagates like a vacuum medium. So it's a very interesting result that we obtained. And it is, another way to understand is that if you look at a magnetic field, then we are always given 3 conditions to define a plasma where the collective effects start dominating. And one of the conditions is that you should compare the collective frequency, that is plasma frequency, with the collision frequency. The collective mode of oscillation should dominate, right? So even in the absence of collisions, in the plane perpendicular to the magnetic field, there is also a need to compare the plasma frequency with the gyro frequencies. Gyro frequencies are like single particle effects. So if they strongly dominate, then this should be the 4th condition, or maybe a 3rd condition, where the collision frequency needs to be, also the additional gyro frequency needs to be supplemented. So many such fundamental results we were able to uncover. We showed that there is an increased efficiency of harmonic generation for a particular magnetic field, demonstrated certain magnetized parametric processes, and recently some very interesting results have been obtained, some of which I will talk. And one of them is about colliding waves in finite size plasma targets, which increase the efficiency of absorption. And a very recent result with Dhalia is that one can generate quasi-monoenergetic, like in an overdense plasma, one always thinks that the plasma will get heated up, and you can only get a thermal spectrum. But what we have showed that there are other possibilities also. Even in the overdense plasma, you can get quasi-monoenergetic electron generation, and that is because of the electron Bernstein waves. And we were able to show that laser amplification can be achieved where the magnetized plasma acts just like a glass or a solid state lens. There are also many other results which I might have forgotten to mention it here. So you can see how diverse one particular suggestion from Professor Cow, and which had in an inside meeting was so much, how diversely this field has spanned in so many areas. So today in my talk, I must have covered a lot of, please stop me. Give me a warning about 10 minutes in advance or something. So this is the talk outline, and I will be talking about irreversible energy transfer from laser to plasma. So some aspects of that I'm going to cover, and essentially about the colliding waves in finite size target, which gives rise to efficient laser energy absorption by finite size targets. These two topics I'll just rush through because I don't think I'll have enough time to discuss that, but I'll just mention this. These all three problems are ongoing. There are many things which can be looked upon in these particular areas. So let me start with two specific pillars of fundamental science. These are the simple harmonic oscillator and the Maxwell set of equations. We study it since class 8. And there was a time when I was in MSc and PhD course, I used to wonder that so many years I'm spending on understanding simple harmonic oscillator. When will I be in a position to learn or understand some frontier level physics? But now, when I'm on the other side, I realize that understanding these two systems really opens up the entire area of frontier science. They form the basis. If we understand this particular two fundamentals nicely, physics would be very, very interesting and clear. Now, if we have a simple harmonic oscillator, when is it applicable? It's simple pendulum, one of the examples, spring mass systems. And there we learned about the concept of oscillation frequency. And this converts kinetic to potential energy and back and vice versa. It's a reversible process of conversion of one form of energy to another. So when we are seeking irreversible transfer, and that's the problem in physics, engineering, etc., and all science and engineering problems, this is one of the core aspects that we look. You have loudspeakers. What do? The sound, the electric signal converts into sound energy. You have microphones. Sound energy has to be converted into electric. So all these transducers, light to electrical, or vice versa, and so on. If you look at all these engineering problems, mechanical to electrical conversion and all these things, most of the problems are related to conversion of one form of energy to another, and preferably irreversibly. Reversible is easy. You can keep having conversion, but to have it irreversibly is a prospect that we need to look at it. And this concept of SHO, etc., are generalized to waves where we have transverse and longitudinal waves, water waves, etc., which give rise to concepts like wavelength and frequency. I don't need to go through these topics to this audience. And I come back to the crucial question. How does an irreversible energy transfer occur? If you look at a pendulum, you want to drive it with a driving force. Even if you drive it at its resonance frequency, and let us say it continues to obey the simple harmonic equation, you will never be able to transfer any energy irreversibly to the pendulum, no matter even if it is in resonance. You can work out the equation of motion. You need a phase slip. And that phase slip typically comes when you have friction. And that's why when you drive it at resonance, it picks up energy. Otherwise, it will never pick up. Mathematics will show you that. And the air friction, the small. So during the time that you are forcing, some dissipative effects needs to be present there. And that is what converts the energy irreversibly from one form to another. So when we want to transfer energy, it is, in a sense, we learn in thermodynamics that there also, when you are transferring heat to mechanical energy, there's a law which constrains it. The work, when you're trying to extract, it is constrained by the Carnot cycle. In these non-equilibrium or small systems, also there are certain dissipative effects which need to be present, so only that you can transfer energy to the other place irreversibly. And that we need to realize. You may recall, how does the pendulum lose its energy? Because of air friction. If you want to transfer energy from the force, that air friction is crucial in supporting this transfer of energy from some other source. You may recall Newton's pendulum. This bob is energetic. It hits it, transfers its energy to this bob, tuck, but then doesn't remain with that particular bob. It comes back, gives it back to this, and the whole process continues. How would you get it transferred to this bob and let it remain there? The process would be that if you cut the interaction, only then this can happen. So in addition to dissipation, you need some other effects. Sometimes non-linearity, collective oscillations, or this needs to be decoupled forcibly. Only then some transfer irreversibly occurs. And this is a famous example. If you have a charged particle, a single charged particle, and you have an electromagnetic wave, it has both electric and magnetic fields. And if it passes through that charged particle, this particle will move while the wave is present. But as soon as the wave passes out, this particle may get displaced, but never acquire a kinetic energy. That's a well-known result that we all know. And in fact, there's a very nice paper by Professor Cow in which it is shown that if the particle is created somewhere in between, the charged particle, then in between the pulse, then it acquires some amount of energy. And how can that happen? That happens when if you have a neutral atom which gets ionized by the electromagnetic field, and in that case both of the charged species may acquire energy. And that is, so it is important that in addition to the electromagnetic field of the laser pulse, you should have the Coulomb potential of a charge, the nucleus, which should be present. So both these together, in fact, can transfer the energy irreversibly. That is what happens in some of the conventional techniques like vacuum heating and J cross B heating, where the sheath potential of the plasma, in fact, helps irreversible transfer of laser energy to the plasma particles. But so the collective effects sometimes favor this particular transfer. In fact, that also happens. And the other result that I showed, that sometimes the collective effects, if you count the magnetized plasma behavior also as a collective plasma response, they need not transfer energy at all, like I showed. It's a vacuum-like propagation for the electromagnetic field. So this, let me skip. So laser energy absorption. Now when we come to that, here also, what we want, you have a lot of energy on laser, and you want it to transfer to a plasma, to heat it up, which is important in case of laser fusion, or to accelerate the plasma particles, electron accelerations, ion acceleration for medical treatment, etc., to specific monoenergetic creations. So you want to do that, and there the transfer has to be irreversible. Some of these modes help. The electrostatic mode helps in this process of transfer. The wave break, if you can transfer the energy of electromagnetic modes from the laser field as it propagates inside the plasma to the electrostatic plasma modes, their wave breaking can heat up the plasma. This is one of the topics I think Sudeep will cover, and he has worked a lot extensively in this particular area. So some interesting observations that we have made, that in order to transfer energy irreversibly, you need dissipative effects. So if the plasma is collisional, it is possible. But laser fields are so fast that collisional effects are negligible. In that case, the collective effects help. Their wave breaking can heat up the plasma. And in this context, the question arises that we should extract as much as energy from the laser fields to the plasma for an efficient process to occur. And it is in this direction that we have uncovered many interesting ideas. One of them is structured and mass-limited targets by colliding waves, which connect with ocean waves and earthquakes, is an interesting idea. A lot of future possibilities are possible here. Magnetized target I have already talked about. Many possibilities have been uncovered, and so on. How do you accelerate particles? The conventional method is a static accelerator. You place a particle, it moves through the potential drop and acquires the potential energy, but then it hits the other plate, gone. Now suppose I keep pulling the electrodes with the speed at which this particle moves. It will always see the potential drop, and it will keep accelerating the particle. And that is where we have an advantage, that if we have a wave which has a speed which is equal to c, the particle's maximum speed is also c, then it can keep seeing a potential drop, and it can keep, if inserted the right location, it can keep getting accelerated. And that's how the particles get accelerated. Example is the particle like human on a sea, what is this, sea wave, where the surfer who keeps gaining energy from the sea wave. And that's the idea which has been used for creation of energetic bunches. And nowadays, the plasma wave-based accelerators have gained a lot of prominence, and they have interesting applications. Experimentally also, This has proved successful. Simulations have played an important role. And it is important that one should have a higher the amplitude of the plasma wave, higher is the energy that can be achieved. Now the plasma wave amplitude is governed by the plasma density, and it should survive. If it breaks up, then that's the limit of the acceleration gradient that you have. So waves should exist, plasma waves, but they will break. So to impart energy or and generate monoenergetic set of charged particles, you need the waves to exist, and there's a wave breaking limit, and the limit of the plasma should be underdense. Only then this electromagnetic wave can enter the plasma. So these are the limits for accelerating a bunch of, creating a monoenergetic set of accelerated particles. But wave breaking, which has a detrimental role here, has also a beneficial role, because once the waves break, it heats up the plasma. So both ways, then you can generate a thermal spectrum. And the wave breaking concept can be understood by watching the ocean, where you see the ocean waves come to the shore, and then with increasing amplitude they hit the shore and they overturn, generating these white foams. So this is the concept which has been applied in the context of plasmas. And as I said, wave breaking is detrimental for creating monoenergetic set of accelerated particle. It is useful if you want to heat the plasma, and it is very useful for, it's needed for fast ignition and laser induced fusion mechanisms, where you want to create an ignition spark, you want to heat the plasma. So as I said, it's a crucial parameter, plasma density. If it increases, plasma frequency increases, and the laser and the ratio of laser frequency to plasma frequency drops, so that you are in the forbidden gap region, and you cannot send the electromagnetic wave inside the plasma to accelerate particles. So then only at the surface interaction you can do. The inertial fusion, the plasma is very overdense for laser frequency, so main action occurs at the surface. But you want to heat it at the core. So then the electron transport and issues like this becomes important. But then there is another way. A magnetized dispersion relation has passbands. So electromagnetic wave can propagate inside a overdense plasma, and then so you can see some of these restrictions can be overcome. But how do we conventionally heat overdensed plasmas? Collisional, right? We know at the surface. The interaction is always at the surface. Or resonantly, if the collision is absent, then you should excite plasma waves, and their generation may result in heating of the plasma. As this diagram, I think most of the students would be knowing here. Sudeep was taking a very nice talk. Okay, fine. So so one of the things I remember when we were here and we were interacting with the TIFR groups, Ravi and MK used to have a discussion on what is the most efficient way of heating a plasma target, and Ravi was doing experiments with the corrugated target. They were found suitable compared to the flat target. We have a paper with him, Sudeep and all, right? And we showed that it generates energetic electrons when the target is corrugated. On the other hand, MK's group had these droplets, and they were also giving very efficient results. But MK was saying that even low intensity laser were leading to a very high X-ray generation and strong energetic particle generation. The question was why, and they used to debate. And I was a silent spectator, and I also didn't know, because there's no difference. If the laser is falling here, it can generate a cup-shaped plasma, as MK used to say here. It can also generate the two plasmon heating here as well as there. So what? Why is it happening? So that was the question always in my mind. And this table shows. So I would now say that I have understood it. And the inspiration came a couple of years, maybe it was 2023, when we were visiting Pondicherry University, and we used to go to the beach. And you can see how important it becomes to have workshops and schools in exotic places, because I got the idea there. All of us were sitting at a very safe distance, and these are young gentlemen, very agile, not like me. You may think that I would, and suddenly a wave came, surprisingly, and we got all drenched up. Why did we happen? I mean, we were watching the seas. There was nothing which could warn us and warn these gentlemen who could have run, even though I could have not run, perhaps, but even they could not do it. So that led me thinking, and I realized, I think it doesn't work. You will notice that when the waves, there's a collision of two waves, it breaks. So when you sit at the seashore, you can watch next time that when the waves come to the shore, the waves increase in amplitude, but you can watch it from. And it crashes on the seashore, generating white water and foam, so basically ending up in losing its energy. But not all is lost. There's a remnant wave which reflects back. And this reflected wave collides with the incoming wave, and if it is of the appropriate order, if both of them are equally strong, they will collide, and that is where the wave breaking will happen. One of them is tiny, then it may hit the bottom and make the up surface more dangerous. So initially you will see a calm sea, and suddenly this comes and hits you. So that's what had happened. So we carried out simulations with, so we want, what is it? So this wave should repeatedly collide. So for that I constructed a small plasma target, spherical, and this doesn't work here, unfortunately, the movie, but you can see it here. So you can see here, this is the kinetic energy acquired. The laser hits this target, and the peaks denote the kinetic energy. The first time, these peaks in fact collide with the collisions. So the first peak occurs when the laser hits the target, and it generates surface waves which go opposite sides. You will see that this peak starts to give up its energy, reversible transfer. But when it collides again, the kinetic energy increases again. Then it reflects from the other side, comes to the front side, collides again. And so all these peaks, in fact, I have shown with this. This is very difficult to observe here, but these coincide with the timing of these surface waves colliding with each other. In fact, there's an additional bulk wave which also propagates, and when they collide, it is at that time that the vast amount of energy is transferred to the particles. So repeated collisions give rise to this efficient transfer, but whatever would have been lost otherwise is now again squeezed out of the wave. And we showed it. Here you can see, yeah, just so you can see these peaks for they coincide with that, and these are the particles, these are the locations where the collisions are happening, and and that is where the maximum transfer occurs. And this also happens that you generate a 2 plasmon decay, etc., which we showed by FFT, etc. So that happens, but it shows that this snapshot picture, you can see that these repeated surface wave collisions as the bulk wave collisions, they are responsible for squeezing out the energy. This is a plot that shows even more clearly. This is the target, top, bottom, front, reverse, electromagnetic beam. So this is the average over y-axis. This is average over x-axis. Electromagnetic wave comes, reflects, a part of it goes inside. There, y direction, there is a part which hugs the target. The kinetic energy, you can see, is more dominantly acquired by particles at the second collisions, and the thermalization occurs also in the second and third collisions. So if you want to efficiently gain and extract energy out of lasers, these repeated collisions are helpful. Now, how does it change between this to this? Here, when the surface wave moves, it is lost because it goes and spans the space. It gets weakened. Here on the other side, when the laser hits the spot, it traverses here, collides again back and forth, and that's why the droplet targets are very useful. So after so many years, when I mentioned it to MK and JK, they had reconciled. They had forgotten about this problem. So this is what happens when lazy people like us get a solution after a long time. So the original people have forgotten their problems, and I have understood it. So the other, I'll not mention, because even in magnetized target, not only do it create a better thermal spectrum, you also get peaks which were able to identify the problem of accelerating monoenergetic beam using magnetized targets. We could also amplify the lasers, because the optical element, which earlier, in the absence of magnetized case, the refractive index is either negative or less than 1, whereas if you have magnetic field, it has solid light dispersion, reflective index. So one can use that. So finally, a couple of comments can I make? So I'd like to pay my personal tribute to Professor Kao. He knew a lot of, some aspects, one particular aspect which I'd like to mention here, which many of you would not have known about him, is not only he was a great scientist, human being, etc., he used to write very well. He used to write poems. And one day I caught him in such a personal moment. I had gone to discuss something and he was writing something in his diary, I was curious. I peeped inside. He permitted it. He was so nice. And I leafed through it, could see profound poems on philosophy, and we discussed that day. And he was so generous in taking the appreciation. Because I had a block, mental block, that I can't write well, and English obviously was too difficult for me. So I was in awe that he writes so well. And sensing it, not only he graciously accepted the appreciation, he encouraged me to write. He said, why don't you also write? And since I had difficulty in writing in English, so I started writing in Hindi. I have now a huge collection about a small girl child, Amoli, and a brother, which I keep writing on Facebook. Many of you who are Facebook friends would have noticed that has received a lot of appreciation. And it is largely due to his encouragement that I realized the words offer such a beautiful, way of expressing your ideas, the play of words, the rhyming, etc. So interesting field in itself. And I started enjoying it. And it was he who noticed it. So he had a capability of observing somebody's potentiality, or even I could have never done this except for his encouragement. So he was a teacher par excellence, mentor and all. And there's a kahawat in Hindi that you should दान जो है सुपात्र को करना चाहिए. शिक्षा का दान he did, and with tongue firmly in cheek, I think I'm deserving student for that. And I still feel that somewhere deep within, I feel that my Gilhari Prayas is appreciated by Professor Kao, who is watching over me, over the cosmos. And I would like to express my humble tribute to him. Thank you very much. Is there a question and answer, or it's fine?
We can have one quick question and then we'll go on. One quick question.
Ma'am, thank you very much for a very interesting
Thank
talk.
you.
I just wanted to, as you said in that, if you keep a chart, but just for my understanding, it's a question. You said that particle is stationary and you put a electromagnetic wave. So it can move but cannot acquire, it can displace, but cannot
It can,
acquire.
yeah.
But when it is moving, so at that time it should have some
Yeah.
by moving.
So it's a reversible transfer. So it acquires energy, kinetic energy moves, but then it is given back to the laser again. So irreversible transfer doesn't occur. Yeah.
Mostly pictures after I joined ETEL. But today we go back to the roots
And there's a wonderful, for those who do not know Professor Kao, this particular introduction by Professor Sen and Dr. Amita Das must have given you a flair of what he was. His incredible ability to connect and work in diverse fields stemmed from one single powerful and irresistible trait he had, which was mathematical physics. So no matter whether he was doing, tokamaks or quark-gluon plasma, he was constantly toying with equations. And we have seen that closely over several occasions. Even while travel, when he is waiting for someone, he would carry a little notepad and keep writing equations and constantly create something out of this. So today I take you to an old work that we did with him, part of my thesis. I found that there is a manuscript which I have not sent out yet, and for a long time I thought that this is much new, but then when I looked at it and looked at the recent papers, it seems that it is still a very valid thing to do. So my talk will be mostly, let's say, deeper insights into physics and mathematics and less on to other aspects that traditionally I have been giving. So there is a very interesting phenomena in hot magnetized plasmas, and these plasmas generally contain impurities. In fact, it's very interesting that the impurity concentration in the solar corona is not terribly different from that in the tokamak, for example, Aditya. Same problems: oxygen, nitrogen, carbon, iron, and same problem. They radiate very strongly, all these guys. Although in the sun they were not created, they were captured by the sun when it ripped through billions of years ago through some nebulous cloud and picked up these things. So we understand corona and then begin to see what processes must be fundamental to understanding of the coronal equilibrium. So I will briefly cover the equilibrium, the physics of the so-called radiative condensation instability, some papers, take you through a rather atomic physics detailed tour, some mathematics and results, and a few personal words at the end. So we go straight to the equations, which is basically MHD equations. Notice that we don't have the electric fields here because electron pressure and electric field balance is imported into the ion equations, which you know very well. So the ion momentum equation is simply del V parallel del T and B dot grad P. B is the ratio of the magnetic field and magnetic field's magnitude, which is a parallel unit vector along magnetic field. The third equation is crucial, which is the energy balance. So we are dealing here with the equilibrium which is kind of slow when it refers to the plasma time scales, not very fast, but still very, very important, and eventually can lead to a sudden collapse. So we have this 3/2 d and dt plus parallel heat conduction, perpendicular heat conduction, heating and losses. That would be the broad governing set of equations. And so the L that I wrote in the red color there is what we need to understand. So impurities in these situations are described by a set of diffusion equations, and we have a standard nomenclature. Suppose carbon, so carbon has nuclear charge 6, so including neutrals it would mean 7 total species. And historically carbon was used everywhere. So that's how the discovery of MARF has come, because of people used those materials which had these kind of radiative properties. So if we look at the impurity equation, diffusion equation of impurities, which is basically time dependence plus d perpendicular del perp square Ci, and then the two terms in the bracket are ionization and recombination. Ionization we write as S, and alpha is the recombination rate, and we have the gains from the previous stage and the recombination from the top stage, so they add to the impurity species, and the losses from that charge state are basically its own ionization and its own recombination. So the equation is rather straightforward to understand losses. So if we look at the atomic processes, we have a few of them, we will need them to know as we go along in this talk. One is the electron impact ionization, which is basically converting a lower charge state into a higher charge state. There is a recombination from the higher charge state to lower charge state, of which there are two. One is the radiative recombination, which is basically a capture, and a dielectronic recombination, which means you need a spectator electron inside the atom, which gets excited during the capture. The capture happens in the high angular momentum states, and then the new electron comes down and gets captured. So only when the spectator goes down, the next one also comes down, and that's how. So this requires obviously one electron already inside the atom. So it's a process which will not be for fully ionized ions. Then electronic excitation, which means an electron hits an atom or an ion, creates an excitation to a higher level, and it promptly comes down. Now here is a little tricky thing. Usually what happens is that these higher excited levels are very short-lived. But sometimes they are long-lived too, which we know very well because we need them in lasers. And then after a while they come down. So if you had a highly collisional plasma, this process is not that simple. But for the cases of our interest, whether it's solar corona or tokamak, the impact and capture, radiative capture. So in all these processes, you lose radiation. Impurities are excited, they emit radiation. The electrons are de-excited, are decelerated, they emit radiation. So there is a Bremsstrahlung radiation, there is a line radiation, and there is a radiation released during the recombination. So there are three broad parts, you can say. So if we want to do it diagrammatically, you can see that the red lines are ionization, blue lines are recombination. And so if we want to do balance, which means that ionization from state I and recombination from state I plus 1 must stay in balance. That is the crux of the corona equilibrium. So start from, say, ground state. In the ground state, you have only ionization goes up, and the first ionization recombination comes down. So the moment you balance that from the ground state to the first state, from the first to the second becomes very easy, because from the first to the second now there are only two processes again to be balanced, which is the ionization from the state 1 and recombination from state 2. And if we then chain this up, you see ratios of ionization and recombination coming into determination of the densities. To get the language clear and eventually probably use it, the unionized level is at the bottom, first ionized is the next, and then think of lithium-like, helium-like, hydrogen-like, and fully ionized ions existing in each of these impurities, and they make a big difference in radiation. So if we look at now the coronal equilibrium's mathematics, we can see that if we balance the charges. For example, this one is the loss by ionization from state 1. C2 alpha 2 is the loss, is the gain from the C2 to C1, and so on. And we take ratios and add up. We will obtain the fractional impurity charge states for all this. And we can then understand them by looking at the rates of ionization recombination. Thanks to Maya for writing a wrapper for ADAS, which this I reproduced recently using the ADAS database. At that time, ADAS database was not free. Now it is online. You can just go and see. But you need a wrapper to read the data. It's a tremendous amount of data there. So what you see here is the ionization rates for each of the ions as a function of temperature and recombination rates. And the ratios of these rates, notice the difference between them. One is almost 10 to the 9 or so, other will be 10 to the 12 or so. So the ratios of recombination to ionizations are small, and therefore it depends on what temperature one is. It's very possible that most of the carbon will be ionized or none of it will be ionized based on the temperature that we take. So this is a piece of work that we did at IPR. The average ion model, I will show you a picture of that. That was built by Russell Hulse and a team. And then we had at that time compared how the ionization and recombination change if you change the fundamental parameters of atomic physics inside, for example, the ionization potential or the fitting parameters. So there are, just for the ionization, there was a model from Culham, there was a model from Lodz, the average ion model, Lodz, and the average ion model. So you can see there is a difference, sometimes going factor of 10. Eventually it comes smaller as you go to higher charge states. So these differences make a impact in your calculations of not just radiation but even the instability thresholds and so on. So there exists a rich variety and unknown here from atomic physics that translates into plasma physics eventually. So to construct the radiative loss function, what we do is we need the fractions of each charge state, and we need each charge state's radiation rate, Ri. And so sum over that gives us the L. And this is the entity that's going to play a role. And there are many charge states here. And if we change, if you have multiple impurities, you have multiple impurities charge states. So we need a model which eventually gives us a simple, insightful view of what is going on. So if we take sum over the fractions which are themselves functions of temperature and Ri, which are the radiation rates, which are also functions of temperature, you can get a composite function G of T. And so the radiation loss simply becomes L, which is density into impurity total. C total is the carbon total impurity, and into G of T. That's the radiation function. And of course, G of T can be specified. So you will see often people writing L as n square times G of T. That's because they have already chosen Ct to be a fraction of the density, which is technically not correct. It's good for short average things, but not for instability analysis. But that's how the field has evolved. So if we then reconstruct the charge, the radiation function's behavior with temperature, what we notice is a negative slope which is between say 10 eV to 50 eV. In this, the blue color is the total radiation rate. We will have to multiply it with the density of electrons and the impurity total, but that is per electron per impurity, and that's in watt centimeter cube. So when we multiply by 2 density, it will become centimeter cube per centimeter cube. The red color shows you the recombination and Bremsstrahlung radiation, which starts approaching the total as we go to higher and higher temperatures. So that plays a subdominant role, but eventually it does play an important if we try to understand why this happened, we need to see what are the populations present at each temperature. And what we see here is the rising and falling of various impurity charge states, which means that if we had a plasma of say 5 eV, that would be the population of the charge state, or most dominant charge state present in the impurity would be that. So you see a rise and fall that is connected with the ionization potentials. As you cross the ionization potential, the impurities get totally evaporated finally, and you see the red colored one, which is C6 plus, which means more or less everything is ionized, and now all the impurity fraction is 1. Notice the last three, they are special. The last one is the fully ionized, the one which shows a peak is like hydrogen like, and the one which light green color is the helium like. These are the impurities which do not radiate much, but at extreme temperatures they would, and the first ones is the one which actually contribute strongly. So look at the old calculations that we did in 1988, we see the same thing. This is a split view of all the charge states, and you can see between C1 to C4, which means neutral to this thing, mostly radiation is large, but the last three, the lithium like, helium like and hydrogen like, fully ionized, have less rate coefficients because they have less electrons. So what happens is that if you want to penetrate into the problem, we need a model, and we at that time conceived of a model with just two effective ions, one group which belongs to the one's electron rich group, which is below lithium like, and the one above. And so we call them as CR and CH, R for radiative and H is a higher state. And then when we do this and club this data together, we can see the red colored curve here, CR, models very well the radiation rates of all the earlier impurities. And if we look at the fractional coronal population, which means we do just CR-CH balance, we can see the CR coming down like a sharp function there, which means that most of the CR has been now ionized into the blue color. And so if we then just use this to understand the radiation's behavior, you can see the radiation rate from CR is rising and falling, and the fractional population is initially 1 and then eventually falls down, the red color. And then we multiply that, we can see that the CR red colored curve does very well with C1, C4, which means that the blue colored one is the one which is, if we were to deal with all impurities, we will have to solve 4 equations, but here you could manage with 1. So basically the whole aim is to reduce the number of equations and provide a straight insight into the problem. So we then write the impurity equations in the new TIM, the 2-ion model, and which gives us another form of the radiation function. Now here we get a new freedom. What we can see is that, notice the SR, which is the ionization rate. Imagine, recall, in statistical mechanics averaging, we know very well that the ionization probability will go as e to the minus ionization energy divided by the temperature, E by T. So what happens is that it's like, imagine a function which is e raised to minus 1 by x. As you go down to x, 0, it drops very, very sharply. And so, and you must have seen that during these curves of ionization, which means that those actually allow you to model very well the step function rises. So if we do a correct model of the ionization using a step function, you are not in error, and you can almost reproduce all the results which people did with the step function, with now understanding of why it is a step function. Okay. So with that, let's come to the straight and obvious things. We go back history. If the thermal diffusion and heating source is ignored, we can see the fundamentals of the instability in equation 16. The 3 by 2 n dt by dt and curly L of t is basically the net loss function, which is the heating and the loss difference taken already. This is a paper by George Field, which is a follow-up of Parker's paper in 1955. We'll be coming to that. So you can see straight away that if you do a analysis here and express L as a perturbation temperature, gamma is 2n by 3 dl by, and this is really everything that the talk is about. You can see just in 2 terms you can capture almost everything, but the mathematical depth to go. Here is a picture which might motivate you. There are many sites which will tell you this coronal rain, which is videos are there. People have captured real as well as simulated. It's actually, you can see the size of the corona and the size of the earth. It's a very huge thing. The amount of magnetic energy in a coronal loop can last us for crores of years actually. So this was a 2012 thing, and here what is happening is that the plasma shoots out extraordinary energy and speed that it carries a magnetic field with it. It is bored down, but it is tied down to the photosphere where there is a strong reconnection and heating mechanism. But as it expands further, it cools and a radiative condensation instability sets in, causing plasma to become very dense. So at that time it's no longer possible to, so it starts flowing along the magnetic field line, falling back to the footprint, and or sometimes straight down, depending on the parameters. So this is a very active field, and so stability of the solar coronal region needs a little bit of deep dive. This is an excerpt from Russell Kohlsrud's book on plasma astrophysics, and you can see let us consider a simple example to make this clear of the interaction of the solar corona with the solar photosphere. Photosphere is at the bottom, corona is at the top, and the field lines have curved and back onto the photosphere. There is a layer in between, of course, which is causing the dissipation. But what you see, and more importantly, is that the frozen in field line is extremely crucial. These lines eventually, the plasma and the magnetic field have certain constant like B by rho or B by rho L or B by rho A, depending on what kind of expansion is happening. It is isochoric or keeping area preserving or something like that. So what you will see is that as the plasma in the photosphere moves along its surface, it carries the footprint along this in such a way that the two plasma elements situated initially at the footprints stay connected by this line of force. And what is happening here is that the tremendous churning that is happening below convectively, which is causing the field lines to get twisted, takes the field lines to their limit of tolerance, and finally they start reconnecting and dissipating that energy into that. So but as you have already advanced into corona, imagine it was Earth's diameter is about 12,000 kilometers. We have about 10 above that. So about 120,000 kilometers above, the plasma is very thin and tenuous. And so most of these assumptions that I talked about the tenuous plasma, the fact that the radiation leaves the plasma immediately, matter there. So this was a very interesting thing where you begin to see the discussion on corona. Here is a platinum jubilee paper of Parker. He had at that time dealt with a hydrogen based plasma. So he thinks of hydrogen neutral and hydrogen plasma and thinks of the stability of that field. It's a very nice paper, very detailed, I picked up few points for you here. You notice that he calculates the 3 radiative points. One is an N, which is the bound transition, which means the line radiation. The next is the free bound transition, which is basically ready to capture, and the free transition, which is basically the Bremsstrahlung. And so you can see when does the character of this is clearly, you can see the dE by dt is less than 0, which means that the radiation is going to increase if you reduce the temperature. It's the negative slope that I pointed out a few minutes back. Notice also the highlighter at lower corona. You see the density of the order of 10 to the 8, the size of the 100,000 kilometers in about 27 hours or so. So by using very fundamental diffusion equations and the foundation of hydrogen, this thing, he is able to try to reach that point of what must be happening in these coronal instabilities. But notice his last sentence here. He says that any conclusive statements concerning the sun, however, probably must wait until we have more information concerning the importance of emission of unhydrogen-like constituents, which is calcium, magnesium, and silicon. And this is very much true. Today we know that these elements make a huge difference. In fact, in this quiet corona and the other corona, iron makes a huge difference. So everything other than hydrogen contributes to these wonderful phenomena. So let's move to the radiative condensation instability. This is a very landmark paper by Stringer, and it is a very fond paper because he was the first person whom we met as a student. I was traveling to a conference and he had come personally to pick me up at the railway station. So Ted Stringer concludes, notice the second picture there, and you know already MARFs are basically multifaceted asymmetric radiation from the edge, which is basically a band of radiation on the inner side of the tokamak. It is poloidally localized but toroidally continuous. So it was a puzzle. But eventually, as you increase the density during operation, this poloidal band starts becoming longer poloidally and eventually connects and makes a completely detached plasma from the wall, and it is called the DP or the detached plasma. So MARF to DP transition was one of the important topics for disruptions. And what Stringer is trying to tell us using a very simple model that we used in corona just now, you notice the last lines there, you will see that as the densities increase, these lines are becoming flatter and flatter, which means that the variation in theta is reducing. It is in fact becoming longer, elongated in theta, and eventually is becoming symmetric. So this was a conference paper by Stringer, but the most, I would say, elegant and the one that changed my view of everything, and this was the time when I was changing the PhD problem in the 4th year. So this was this is a paper which Professor Kodges said she should take a look at this paper because he knew we were working on radiation, and so this was the one I presented, and this was a very nice paper. So what it does is it takes a step function as a model for radiation, calculates the radiation of a cylindrical column, which is heating in the center, radiation at the edge. Very simple. But there is a tremendous physics in this paper. So if you now look at these 3 equations that I showed here in linearized equations, which is basically density perturbation, velocity perturbation, and a combination of them giving us k parallel square Cs square upon gamma square plus k parallel square Cs square, which is basically comparison of growth rate with the ion sound time. Okay. Now, if you have k parallel, which means in the case of tokamak it would be b theta upon b into k. So the the flow must occur along the field lines in order to have K parallel. So, unless there is a poloidal mode number to the instability, which means there is a variation in the poloidal direction, there is no M and there is no K parallel in this case. So, what happens in this particular case is that when you do the equilibrium and calculate the temperature profile, the correct way of doing that is demonstrated in the paper. First of all, you solve in the inner region, solve in the outer region, make sure that the derivative is 0 at the center because that's the peak of the temperature. Make sure that the derivative is 0 say at the edge because it's very low power going out to the edge, and we match the solutions in between, which is the layer thickness, which is basically delta. So, we are somewhere close to the edge, about a delta distance away from the edge inside, and we are matching temperature and temperature gradient. Now, this particular thing is extremely important, in these instability analysis. You will see this happening in the tearing modes also, and in fact, these codes are called delta prime solvers because they want to match and obtain the eigenvalues or obtain the dispersion relation by this matching of the derivative. It sounds simple, but actually when you are matching the derivatives, you are actually obtaining the dispersion relation. So, when this was done, it was only then that one could find that M equal to 0 mode is stable, because people always ask, why doesn't it happen everywhere simultaneously? Why is it poloidally asymmetric? That's because the equilibrium doesn't allow it to do so, and that is because equilibrium's data gets entered into the dispersion relation, because you cannot solve the equation as just a Fourier series. You have to solve a mode equation in the radial direction. So, the perturbation has a structure in the radial direction, and that was the beauty, and it's such a simple, anyone could do this even in the PhD coursework. It's such an amazingly simple thing and rich with so much physics there. So, this was a very interesting paper. So, when we extended this work to include the non-coronal effects, we had to introduce the impurity dynamics into the problem, because impurities are no longer just ratios of ionic states, but they diffuse, they have time dependence, they have gradients, and so once you include that physics, what you see is that you have to then intuit the models of how the ionization or recombination would be proposed. Okay, so we have to therefore necessarily introduce normalizations, which are basically crux of the physics. Here, for example, you can see the quantity phi, which is basically an impurity density, but it is normalized to its coronal value. The psi is a temperature which is a ratio of the temperature at the radiation layer thickness. LC is a critical radiation rate beyond which the equilibrium won't exist. Rho square is the ratio of the L0 to LC, which is a fractional radiation rate, which you have experimentally put onto the tokamak, L0, whereas LC is a characteristic of the tokamak for that particular parameters. So, as you go on raising rho, which means you are injecting more and more density into the plasma. H is the heating rate, which is basically balanced by the diffusion. You can see the H equal to 4 chi Tc upon A square being a reflection of the energy confinement time, and it's basically just the energy confinement time expression. The fractional delta, which is the layer thickness, and M square is a parameter which is indicative of the ionization rates. So, after reduction into physics, you just get these two equations, which is psi prime double prime, which is 2 rho square phi, and this. Of course, I will not go into the details, but just tell you the basic physics here, that the beta square that you have is the ratio of the time taken to diffuse across a layer, and therefore beta tending to infinity corresponds to coronal equilibrium. And we need a new parameter, which is layer recycling fraction, which is basically the ratio of the impurity diffusing from the boundary inside the layer. It's like injecting impurity inside the boundary layer, constantly driving the coronal equilibrium away from its basic equilibrium and going towards non-coronal things. So if we use these equations, we can recover very easily previous results by setting various limits. For example, phi equal to 1 is just the coronal equilibrium, and psi equal to this quadratic is the results from Drake. And if there are 3 parameters here, so diffusion, radiation, normalized radiation, and the gradient of impurity, which characterize the whole set of solutions. So the most important results are that the radiative layer widths are smaller. Non-coronal effects do not change the fundamental that m equal to 0 is stable. And the general effect of time dependence and diffusion is to weaken the instability. So it will be a greater threshold you will need for that. So these were the results. I have taken a photo of that. So you can see the profiles of impurity radiation, which are, instead of sharp, they are becoming smoother. The last 2 curves show you the temperature profile and the layer width. Layer widths are slightly smaller than coronal. And this work eventually went on for the 2-dimensional solutions also. And this was a very interesting thing. We were working on this 2-dimensional solution for a long time, and sometimes it was almost 3 o'clock in the morning. Professor Kaur was also there when this calculation was going on, whether it is converging or not. So we constructed an analytical model for that. And then after a few days, he called me here in this room. He said, Shishir, we have a solution. So he remembered these island solutions, which were done for tearing modes and others. So, and on the board, we actually did this calculation and obtained the critical radiation rate, obtained the solutions. And then after some time, I found this paper by John Shivell. And here is an experimental paper of bolometer array in TFTR, where the radiation was reconstructed during the MARF-DP transition. So first the MARF was created, and then eventually it becomes poloidally symmetric. So these are 3 time stops, and we could actually reconstruct this whole thing exactly. It's qualitative because we don't have the same ratios of radiation and same parameters. But this was a very interesting paper, and this was one paper where he actually said good words to me directly. Here I should say that nothing happens without a guru. I don't know whether you can see Professor Kaur there. There's a white head behind. This was a meeting here, and this was I was looking for a photo with Surjalal Sharma. Unfortunately, Surja is not among us now, but he was the one whom I had joined, and we had done atomic physics at that time. The paper, the report that I showed you with Suresh and Dham was actually when we were building the impurity transport code in Punjabi University in Patiala. So I stayed there for a month, and they had we wrote lots of codes and coefficients for that because they were good in neutral gas modeling and that. And so we created a number of atomic physics benchmark also, which I just showed you. Here is a picture which shows Nikhil, and I think next to Professor Kaur behind is Parvez. I think, but one has to zoom into that. So here are some memories. This was a talk which we had given somewhere. What you see on the right are Professor Kaur's comments on the manuscript, where take this into account, etc. Bottom left is Russell-Hulse handwritten notes. Russell-Hulse is the famous Nobel Prize winner, Hulse-Taylor pulsar, 1993 prize. So when we say, yeah, it's our Hulse, process cause reaction was that. So this handwritten notes are indicative of extraordinary meticulousness and clarity, and I think there are many plasma phases you can download. For example, I think there was one in Madison whose notes are available, handwritten notes are available. So cleanly written and very in depth, and this is all like a collection of formulae including Gaunt factors, various approximations, and how to construct the ionization potentials, recombination coefficients, radiation excitation levels. And the bottom right is the computer programs, and this is actually 1986. These large sheets on which we used to do calculations. So I think that with that I come to the end of my talk. Thank you very much. Yes, Mani.
So most of the time we ignore the cyclotron emission. Why is that not contributing? Because I happen to see a graph in which they plotted the wavelength versus radiation from a token.
It is not negligible in about 10-20 keV. In demo we have to take that into account, demo and fusion reactor, but it is extremely important also in the neutron pulsar magnetospheres. So it is a strong contributor to radiative loss, but that's because it's the only thing that is there. There's no other player there except unless you go very close to the poles of the neutron star. Yes, Jaydeep?
You said that you can generate acidity at one location and then it fills up the whole potential periphery. So what do you require to do that? Means
Raise the density, go towards the disruption limit or density limit. The environment and effectively the radiation to its limit. It starts either the dP is formed or it is disrupting. dP actually is a stable state preceding disruption, sometimes because the MHD equilibrium has been established properly. The radiative layer has provided the necessary boundary conditions for the heat and the current density profile. So the shrinkage of the current density profile should not be so much that you trigger a low m number disruption.
So when you increase the density, you also require to maintain the same plasma to increase the power, input power.
No, the input power is same in this case. It is the L by LC which is changing, which means that you are increasing the radiation, or you are increasing, let's say, the impurity density. So the outer layer starts radiating more and more heat. Finally, it reaches a point where it radiates all the heat that is coming from the core. Otherwise, heat was partly going by radiation and partly by transport. But we were increasing the capacity of that outer layer to radiate most of the heat. And by the time we hit, say, 90-95%, it becomes unstable. Because then even a fine fluctuation in the temperature causes a current density fluctuation, which causes a MHD perturbation.
And last question is that why you are calling it, it is also m equal to 0.
M equal to 0 happens only at the end. M equal to 0 becomes unstable only when you have reached the critical.
But that is stable. That's why it should then.
No, the before that is stable. The problem is there is no reason why it should be stable. It is stable because equilibrium has, because there is an equilibrium. So equilibrium's heat flux makes sure that m equal to 0 is always stable until the equilibrium itself is about to collapse. The key physics behind condensation is that, suppose imagine a field line on which you have suddenly introduced a cooling perturbation. So, because of the nature of radiation, the cooling enhances cooling further because there is a negative slope. So, this is thermal part of the instability. But what happens is that you have now also asked for pressure balance, because gamma is much smaller than k parallel square Cs. So, if you increase the density, if you lower the temperature, you have to increase the density, because Nt is same. So, if you have to increase density, that further increases radiation, because radiation is proportional to n or n square. So, that is the add-on. Condensation is an add-on which comes in for, but for that you need m equal to 1 or 2 or k parallel. You need k parallel for that. So, the condensation starts after you have reached almost the critical point. But of course, in corona, you have the condensation all the time, because you have the heat sources at the corners, and as the fluid lifts, it cools by various processes and particularly by radiation. So, it is going to accumulate a lot of condensation until it becomes weighty enough to start falling under gravity.
So,
Yeah.
so in the case of a stellar atom, we saw the detachment. The radiation from hydrogen itself is almost 3 times of a carbon.
Hi.
So, one reason is that the stellar atom which I am talking about is WS1AS, in which we don't have a continuous diverter, we have only an island diverters. But the radiation from Balmer spectrum was much more than the carbon. There also we
That may be because they have significant neutrals at the edge.
Yeah,
Ah.
that's why the detachment happens. So there's a lot of
Neutral based detachment, yes. In detached diverter, in fact, I did not talk about it, but the X point radiators are like driven MARFs. You have already created a condition for MARF there, so it's going to happen there only. The puzzle here was, why does it form only on the inside, and that is because the thermal conductivity has a certain theta dependence, which there are papers which we have and what others also have, which show why it is localized. So, poloidal asymmetry is definitely guaranteed, but in-board side location has to do only with the chi-perpendiculars dependence on theta. Okay.
Corona model, we assume that particle diffusions are neglected along with the time.
Yes.
So, while calculating the non-corona model, we took the thermal diffusivity.
Particle also.
Particle also.
Yes.
So that is also considered when we are.
Yes.
Yes. So that contributes eventually to the.
Yes.
Radiation loss.
Non-coronal effects apparently reduce the drive and all that, but they will play a very big role when you do massive gas injections, shattered pallet injections, or neutral gas sudden injections for controlling disruptions, or VDE control. There this radiation is huge. So, and you are far away from the coronal equilibrium, which means that now you can be very much strongly radiating, because a low Z impurity is already inside where it should not be. So, you can have radiation driven collapses because a large flux of electron rich impurity has suddenly found its way inside the tokamak, and we need that because that is our actuator. The non-coronal effects give you a handle on controlling, an actuator on controlling a sudden collapse or thermal collapse.
Main point seems to be lower the temperature, higher the radiation.
Right. That was a feature of the coronal radiation. In the coronal, if you take coronal equilibrium, that's what you will get. You lower the temperature, you will have higher radiation because you have electron rich impurities there.
Keep the pressure same, you increase the density,
Ha.
further reduces the temperature.
It will further reduce.
Increases
Ha.
radiation.
It's a double drive. Radiative instability is one, and radiative condensation instability is an add-on which comes from this. But for that, as you said, the Nt parallel, N tilde equal to minus T tilde, for that you need a parallel conduction. And parallel conduction is possible only when there is a poloidal mode number in this particular cases. So, it's a interesting.
Density, you have collisions are also increasing.
Where?
Increasing the density. So always that will means if it is something like going to collision and radiating mode.
Yes, but here the densities are order of 10 to 13, 14. So in the diverter detached case, yes, because you have almost a sub EV temperature, and neutral gas alone is taking the load of the plasma. I mean, imagine a lot of plasma coming in with heat, and it's all going via ionization. So neutral gas is effectively blockading the plasma flame from reaching the diverter. But such boundaries are dynamic. There is no fixed boundary where the neutral gas stops the plasma. It's a diffuse boundary, and therefore it is rich and open for instabilities, especially coronal radiative ones. Because there the rates of atomic rates are extremely sensitive functions of temperature. I mean, 1 eV and 2 eV will make a huge difference in radiation. So
There is a dependence on the rate of rise of density.
rate of rise, no, I think that may be related to the rate of current profile contraction. If you rise too fast, then it is okay, but if you allow the current profile to contract while rising, then you may not even reach that. It will start collapsing much before that. Usually current diffusion time scale will be slower than thermal.
In your memories, I saw a computer printout.
Yes, it says, I still have that, it says S. Deshpande 1986, and it has
It has not become brittle.
no, it is becoming brittle. I was able to barely turn the pages of that presentation. That goes straight into 19.
There on that.
Yes, sir. There are still the slides written by me. The one photo that you showed in which Professor Kao is writing slides, those kind of slides are also there. Drawing.
Have those in library, like say you mentioned about a note of somebody's.
Yes, Russell, yeah, we can put that in the library. I think it will be.
We have quite a few handwritten manuscripts.
But it is good to have the plasma physics notes for research scholars, and I think Princeton's Greg Hammett and Madison's, I am forgetting the name, but they are handwritten notes. Andre Rogister, now I remember the name. Andre Rogister's notes were with Raghavendra Singh. So, Jim Callan's notes, correct. That's the one. That's available download. So I think students, or in fact everyone should download them, because they are done to the depth and detail, where everything is written, and even hand sketches are available. Huh? Very neatly written, and hand sketches are available. I mean, you can, while explaining, although the printouts are there and nice computer, but still it is handwritten because it has a marker, and you can then understand certain things there.
He has some YouTube lectures also.
Ah.
He has converted to books also, but
Yes.
those are not.
Look at his solutions of the Brzezinski equations, where he actually solves for the resistivity and viscosity. So there you will see this. But coming back to that, Professor Kao's fabulous ability was to understand anything in terms of the equations that he had a grip on, and so I remember that he used to go to Saturday in those days to meet Dr. Parikh in those very early days. So sometimes some meetings were held there, our meetings. So that's how we knew. So he would try to convert that new field's equations in his own terms, in his own way. And so it's what is important take home for us is that we should interpret in our own way. Until you are convinced and until you write your own equations, it will not be clear to you. So that's the way to get to the core of physics. Thank you. It was very nice. I forgot to thank Saroj and Sudeep and Tapas ji for making this, and it was good to meet Amita and Jiten after a long time. Thank you.
The poster session starts at 2:30. So we will be back here.
Thanks. Yes.
Thank you.
मैं जस्ट ये नहीं चाहिए मुझे, इनको इनवाइट ही करवाना। अच्छा ऐसा है, अब आ जाइए टॉक देने के लिए। हेलो, स्क्रीन नहीं है? Done? Session. So I think we had a great poster session. So in this session we have a talk by Professor Sudip Sengupta. So I would invite Professor Sudip to please come and deliver his talk.
Okay. So good afternoon, colleagues and friends and students. So in the morning, we have heard two excellent talks, theoretical talks by Professor Das and Professor Deshpande. Maybe I should call Amita and Shishir. That's more easy. Yeah. So we had excellent talks by Amita and Shishir. So today I'm going to talk about a very old work which I did with Professor Kao and his collaborators. It's an experimental work which was done, the experiment was done at TIFR, and we did the theoretical modeling. This work, you can publish hundreds of papers, but there are some problems which are very close to your heart. This one took a lot of my energy at that time, and we spent a lot of time trying to model this data. And after the success, okay, maybe I should first discuss the work, then I will talk about other things, okay. So the work was done the experiment was done at TIFR, and we did the theoretical modeling. So I begin by describing what is plasma wave. So one of the fundamental electrostatic mode of oscillation in an unmagnetized plasma is a plasma wave, is plasma oscillation, as simple as that. So study of large amplitude plasma waves has been an active area of research for more than 50 years, or maybe more than 60 years now. One of the well-known results which is associated with the nonlinear behavior of these waves is that beyond a critical amplitude, the plasma cannot sustain coherent motion and the wave breaks. This is a very simple result which has been obtained analytically. Okay. So the wave breaking amplitude is reached when the oscillatory velocity of the electron matches the phase velocity of the wave. A very simple result. Okay. So there have been some experiments which have shown that when this condition is satisfied, then you actually get wave breaking. One of the experiments is in dusty plasmas, but to the best of my knowledge, that paper was published in 1992. But to the best of my knowledge, I have not seen any other paper on wave breaking which have been seen in dusty plasmas. Maybe on dusty plasma, but this is what the thing is. There have been some paper which I will talk about later, but they are probably not right. Okay, so I'll tell you what's the problem with them. Okay, so let's go to the TIFR experiment. So we begin with the experimental schematic. So it looks something like this. So the experiment consists in, there is a main laser pulse. I will shape change. Okay, I'll change the shape. So there is a main pulse of intensity 10 to the 16 watts per centimeter square, having a wavelength of and 100 femtosecond pulse width. So this main pulse is incident on a target at an angle of 45 degree, where there was already a plasma formed using a pre-pulse. So you first shoot a pre-pulse which has intensity which is 50 times lower than the main pulse. So the pre-pulse falls on the target, pre-pulse is incident normally on the target, it forms a plasma, and then you shoot a main pulse after a time delay. So the experiment consists in measuring the reflectivity of the main pulse using this photomultiplier tube and the second harmonic component of the reflected light using this photodetector. Okay, as a function of time delay between the main pulse and the pre-pulse. So as the pre-pulse forms, the plasma will expand. So basically you are measuring the reflectivity of the light pulse and the second harmonic radiation as a function of time delay or as a function of plasma density scale length. Okay, right. In addition to the measurement of second harmonic and reflectivity, they also measured X-rays coming out of the target. So when a main pulse falls on the target emits a copious amount of X-rays. So that X-rays is measured using a sodium iodide detector. So this was the experiment. So what they found is the following. Is the experiment clear? Okay. So what they found is the following. They found that between 30 to 300 keV X-rays. Okay. So what was found is that as time increases, the X-ray time increases means the time delay between the main pulse and the pre-pulse increases, which means the scale length increases. They find that the X-ray yield increases, reaches the maximum and then slowly scales up. Okay. And second harmonic, which is defined as the intensity at the second harmonic divided by the square of the intensity at omega. Okay. So that also shows that at small values of time delay, the second harmonic radiation is low, and at large values of time delay, the second harmonic radiation is also low. But in between, the second harmonic rises, but there is a peculiarity which is seen. See the thing, at 24 picosecond, which is our main point, 24 picosecond, the X-ray yield enhances by 2 orders of magnitude compared to the baseline value. How is the baseline value done? It is normalized to the radiation emitted without the pre-pulse. Okay, so it is just radiation obtained with the pre-pulse and main pulse divided by the radiation obtained with the main pulse acting alone. Okay, so what they find that at 24 picosecond, the X-ray yield enhances by 2 orders of magnitude, whereas at the same time, the second harmonic radiation shows a dip. Okay, so this was the puzzle which they wanted us to explain. Okay, so understand the X-ray result. One simple model is that if there is copious amount of X-rays coming out at 24 picosecond, then you should see large amount of electrons also. Okay, so what they did, they measured the X-ray count as if this is distribution of X-ray. So amount of X-ray photons lying between E and E plus DE versus E. Without the pre-pulse, they see only hot electron spectra of only at 3 keV. So very low energy. What low energy? 3 keV X-rays. Whereas with the pre-pulse at 24 picosecond, they see 2 kinds of energies. One slope at 5 keV and another at 37 keV. So very strong X-ray emission at 37 keV. So you can see that statistical weights. So without the pre-pulse, the T2 upon T1 ratio is of the order 10 to the minus 5. Whereas with the pre-pulse, the ratio of the higher energy component divided by the low energy component is 10 to the minus 3. So you see a significant high temperature component of X-rays. Now it also turns out that this 37 keV, okay, this was the formula which was used to fit the lines. So this came later, okay, right. So with the 24 picosecond, there is a burst of which are interacting with the plasma and generating X-rays. Okay, so and it was also found that this 37 keV is consistent with the Beg's formula. Now Beg has given a formula, basically a scaling relation, that given the intensity of the laser light, what is the temperature of the hot electron component. This you can calculate, and it turned out to be consistent with the Beg's formula. So experiment is all fine, okay, and Beg formula is also fine. Now let us try to understand the results of the experiment. What is happening? Okay, so let's look at the very simple theory which is taught in basically first year PhD coursework. So when a p polarized light is incident on an inhomogeneous density profile, p polarized light has a component of electric field along the density gradient. So this reflects at a density, electron density, which is critical times cos square theta. Easy to show. Theta is the angle of incidence. But what happens is, I think some of the symbols have gone. Okay, I'll explain. Okay, so there is a laser light which is falling on a inhomogeneous density profile. It's a p-polarized light. So there is a component of electric field which is along the density gradient. It reflects from the critical layer, before the critical layer, given by nc cos square theta. There is a component of the electric field which tunnels to the critical layer, and this electric field is oscillating at omega. At the critical layer, we have a natural frequency which is omega p. So what will happen? This electron will driver. So at the critical large amplitude plasma waves because of this driver. Okay, this is called resonant amplification of plasma wave. In the simplest mechanism of heating a plasma using an electromagnetic wave. Okay, right. So if it's an ordinary wave, you excite plasma wave. If it's a magnetized plasma, you excite upper hybrid wave. Wave could be X mode, anything. Okay, but the mechanism is very simple. You have a component of electric field which oscillates the electrons at the critical layer. Critical layer electrons have a natural frequency which is omega p, and omega p matches omega, and everything is resonant. Okay. So now plasma wave is excited by the incident laser. Now this plasma wave, we are now thinking of a model. So this plasma wave now damps either through collisional mechanism or through collisionless processes. Collisionless process could be Landau damping, or could be a process where the plasma wave gets carried away because of finite temperature. Okay, so this wave damping, the energy of the wave goes into electrons, and these electrons then through Bremsstrahlung generate large amount of hard X-rays. So this is a very simple model. Energy from the light wave goes into the plasma wave damps, the energy from the plasma wave goes into electrons, and electrons finally generate X-rays through. Okay, so let's look at this figure again. Forget about this. Let's look at this figure again. So at this point, the electrons are, the light wave is oscillating the electrons, right? And it is producing a density perturbation. So that density perturbation coupled with the oscillating electron velocity generates a current at 2 omega. So this you can show by combining the Maxwell's equations with the continuity equation and the momentum equation. You can generate a second harmonic current. You can actually here, you see this is the electron velocity, and this is nothing but delta n, gradient times x, the electric field, right? So this is xos dot grad gives you a delta n. That delta n multiplied by velocity multiplied by the electron charge generates a second harmonic current. So this second harmonic current, and there is another term which comes from the Pondor motive force. But if you see that this ratio of these terms is proportional to epsilon. Since at the critical layer epsilon goes to 0, the second term is not dominant. It is the first term which is dominant as compared to the second term. Okay, so at the critical layer there is maximum contribution from the first term, and you should see a large amount of second harmonic generation. So simply put, the light wave generates a plasma wave damps, gives the energy to the electrons through Bremsstrahlung produce X-rays. The plasma waves interact with the oscillating electrons, generates a second harmonic current, and second harmonic current generates second harmonic radiation. So larger the energy of the plasma wave, larger should be the amount of X-ray emission and second harmonic emission. So this is a very simple-minded theory. So at the fundamental level, so the physical mechanisms responsible for generation of hot electrons, hence hard X-rays, and second harmonic radiation are intimately related to the dynamics of electron plasma waves, which are excited at the critical layer through the resonance absorption of incident laser. Okay. So it appears that larger the amplitude of the excited plasma wave, larger should be the emission of hard X-rays, and larger should be the emission of second harmonic. So you should see, if you measure X-ray as a function of time delay and second harmonic as a function of time delay, both should peak at 24 picosecond. Right? A simple-minded physical model says this. Okay, but we see some anti-correlation. Now, Okay, so amplitude of the, okay, now we go back to a model of light absorption. Okay, we see that the absorption as a function of L by lambda, as a function of time delay or the function of scale length, peaks at a certain value of specific value of scale length. So for a given angle of incidence, there is a particular value of L by lambda for which the absorption peaks. This is standard Denisov theory, and some of the first year students understand this. Okay, so absorption as a function of L by lambda is given by this. Now, so if you measure the reflectivity of the light wave, you will see that at specific value of L by lambda, the absorption is maximum, minimum. So what was measured is, this was another experimental result. They measured the reflectivity of the main pulse and found that exactly close to the 24 picosecond, the reflectivity is minimum. Okay, so at 24 picosecond, maximum absorption of light wave occurs. So maximum energy should go to the hot electrons, maximum amount of hard X-rays should be emitted. Okay. At 24 picosecond, large amplitude plasma wave is excited, hence the second harmonic current should be large, and hence second harmonic radiation should be large. Simple theory. Okay, right. So strong resonance absorption implies large plasma wave excitation, strong second harmonic generation, and strong X-ray emission. Okay, right. Okay, so just for a side thing, that since the angle of incidence here was 45 degree, so you can calculate the scale length required for resonance absorption to peak. Okay, using this formula. Actually, it peaks at value of tau equal to 0.8. Right. But there is another phenomena, right, through which a wave can break, through a wave can damp. All this process which could be a Landau damping. But there is another way through which the wave can break. Dawson has shown that by doing a full nonlinear analysis, that there is an amplitude limit for the plasma wave. So above that limit, if you increase the amplitude of the plasma wave, a time comes or a value comes when the electric field gives unphysical multi-valued solution. The Poisson's equation gives you unphysical multi-valued solution. Now this is, at that point, the wave loses its coherence. It's very simple that if you have a longitudinal wave, right, where the constituent particles are oscillating, okay, and the wave is also moving in this. So particles are oscillating in the direction of k. Okay. Now suppose it happens that the oscillation amplitude becomes equal to the wavelength itself. At that point, you know, the neighboring particles will sit on top of each other. They'll hit each other, and resulting the wave will turn. Okay. So this is the point when the wave breaks. So the plasma wave, so you see here, so plasma waves amplitude is limited by this condition. When the X oscillation becomes equal to lambda, or equivalently when the phase velocity, oscillation velocity, becomes equal to phase velocity, at that point the wave will break. Okay, so wave will damp through a nonlinear process which is called wave breaking. Okay, so if you try to drive waves above this limit, wave will undergo a catastrophic wave breaking process. Okay, so now the resolution of the puzzle is the following: a hand waving resolution. We'll do the modeling later. So for sufficiently high laser intensity, at the peak of resonance absorption, the excited plasma wave will most likely satisfy the. So what must be happening at 24 picosecond? That at 24 picosecond, the plasma wave amplitude is so high that the coherent motion is breaking. So physically, at the wave breaking, bulk of the background electrons are instantaneously brought into resonance with the wave, and accelerated velocity is comparable to the phase velocity of the wave. See, what happens is, at that point, when your oscillation velocity equal to the phase velocity, a large number of harmonics gets generated. Okay? So phase velocity of the harmonics turns out to be close to the thermal velocity of the bulk particles. See, if you generate higher harmonics, omega by k will decrease. Okay, higher the k, smaller is the omega by k, resulting in So as omega pi k decreases, a point comes when it touches the bulk of the distribution. At that point, all the electrons instantaneously come in resonance with the wave, and that is what happens at the wave breaking. So energy of the wave goes into hot electrons, and you generate a large amount of X-rays. On the other hand, if you want to have second harmonic emission, you need second harmonic current. If you need second harmonic current, you must have a wave. And if the wave dies, then you cannot have a second harmonic emission. So what is happening is that because the wave is breaking, the second harmonic is suddenly damping, because second harmonic current is suddenly vanishing. So this seems to be the indication that the wave excited at the critical layer is undergoing wave breaking. Okay, so this opposite behavior of second harmonic generation and X-ray emission is an indicator of breaking of plasma waves. Okay, so this is all still on all talk. Okay, it's all talk. Okay. They also showed that this is another, this simultaneously to show that it's actually because of the plasma wave. So what they did was they rotated the half wave plate at the correct time delay. So what they did, they changed the polarization of the main pulse from P polarization to S polarization. And they found that the integrated X-ray yield decreases, because S polarized light, for the S polarized light, the electric field is perpendicular to the plane of incidence. So it will not excite a plasma wave, and hence no X-ray generation. So this is another proof, experimental proof, that the X-rays are being emitted by electrons which have taken energy from a plasma wave, and the plasma wave has been excited by the incident light wave. Okay, so now we start modeling. How do you model the X-ray yield? So we start with a very simple formula. Okay, the formula is given in Kruger's book, any book. Okay, so the X-ray yield is an integral over effective collision frequency multiplied by the energy density of the plasma wave. Very simple relation. Okay, so this is nu effective is the effective rate at which energy is drained out of the plasma wave, and Ez is the electric field associated with the plasma wave. Right? It's easy to understand. Ez square by 8 phi is the energy density in the plasma wave multiplied by a collision frequency integrated over all space. This is the simplest formula for X-ray yield. Now, if you go through Kruger's chapter, third chapter, it turns out that the absorption or the X-ray yield actually becomes independent of nu effective. Okay, physically it's very simple to understand that at the critical layer, your plasma wave amplitude increases as 1 upon nu. Okay, and the width of the resonance region is proportional to nu. So nu times nu becomes nu square, and E by nu means 1 upon nu square. Here the nu cancels, and this whole integral becomes independent of collision frequency. This happens only when there are linear damping processes. But in general, this is where I think Professor Kao gave a very nice idea, that in general for nonlinear damping processes, the absorption should become dependent on the intensity. Okay. So let me introduce these key ideas. So amplitude of the plasma wave, instead of increasing as 1 upon epsilon, gets clamped to a value of the wave breaking limit. See, in general, what do you see? See, for example, take a homogeneous plasma. Okay, take a homogeneous plasma and take a light wave. It simply propagates as long as omega is greater than omega p. Okay, you have omega square to omega p square plus k square c square. Okay, you take an inhomogeneous plasma, the light enters, reaches the critical layer and reflects. So as it reaches the critical layer, its group velocity decreases, wavelength increases, and the amplitude of the light wave increases. Okay, so at the critical point, you will see that in fact this, for a linear density profile, this is given by a Airy function. Okay, let me try to explain it this way. I don't want to go to the full maths, but you have an inhomogeneous profile. Okay, light wave is entering, its wavelength is increasing, its group velocity is decreasing, its amplitude is increasing, and that can be modeled by a Airy function. This is an exact solution. Okay. Now consider a plasma wave. For a plasma wave, the dispersion relation is omega square to omega p square plus 3k square v thermal square, very similar to k square c square, right? So if you have a plasma wave entering an inhomogeneous plasma, this should also give a Airy profile for the plasma wave. If you do that, the wavelength of the plasma wave near the critical layer turns out to be lambda d square L to the power 1/3. In fact, this was the key input from PK curve. I'll tell you, if you do a very rough calculation, you can show that the light wave, when it interacts with the inhomogeneous plasma at the critical layer, its wavelength goes as lambda square L to the power 1/3, where L is the density scale length. If you have a plasma wave, it goes as lambda d square L to the power 1/3. Equations are exactly similar. Dispersion relations are mathematically similar structure. Okay, right. So if you do that, the wave breaking electric field turns out to be this. It is same as this expression. If I go back to my first slide, EE by, if you write V phase as omega by k, this is what you will get. And k is 1 upon wavelength, 2 pi by wavelength, and that wavelength is lambda d square L to the power 1/3. This was one key input. And second thing, what was predicted or guessed that the collision frequency should become a function of L by lambda. Okay, this was actually first intuition came in TIFR. Okay? Collision frequency should not remain independent of L by lambda, but should become a function of scale length. Okay, with these two inputs, now you can calculate the X-ray yield. So what you do, you divide the integral into two parts. First part is just the linear absorption, and second part is wave breaking field. So you start from the point where the wave breaking starts to infinity integrate. Okay, right. If you do all that, it turns out that the X-ray yield is proportional to scale length at the critical layer multiplied by some unknown function of scale length. This much we can say, right? So X-ray yield is a function of scale length multiplied by some unknown function of scale length at the critical layer. Okay, right. This unknown function we will determine later. Okay, so at the moment this is what the model is. Write down the Maxwell's equations to second order, and you can show that the second harmonic, in fact, it was shown by Erokin in 69, that the second harmonic yield is also a function of L by lambda. Okay, so phenomenologically, both X-ray yield and second harmonic efficiency both are functions of L by lambda multiplied by some unknown function of L by lambda. Okay, so here nu effective by omega is an unknown function of L by lambda, and rho is nothing but 2 pi L by lambda. So you can see both second harmonic efficiency and X-ray yield are functions of L by lambda multiplied by some unknown function of L by lambda. Whereas these constants, you can forget they are of functions, these constants are of order unity. So both X-ray yield and second harmonic generation efficiency depend on plasma scale length, which means they depend on the time delay between the pre-pulse and the main pulse, and the effective rate at which energy is drained out of the plasma wave, that is nu effective by omega. Now how do we determine this unknown function? So this is the main puzzle. Okay, right. So now this can be deduced from the reflectivity curve itself. So you look at the reflectivity curve and find out where is the reflectivity dips. You see that the reflectivity dips at 24 picosecond. So I know that since it's a resonance absorption process, the reflectivity or the absorption must follow the Denisov theory. So Denisov theory tells me that the scale length at the critical point follows this relation. So for a given theta, I know the angle of incidence, which is 45 degree. So I can calculate the density scale length at 24 picosecond. So density scale length at 24 picosecond divided by 24 picosecond gives me the velocity of expansion of the plasma front. approximately. Okay? And it turns out that at these intensities, which is 10 to the 16 watts per centimeter square, this kind of velocities have been measured by other groups also. So velocities of the order of 10 to the 5 centimeter per second. Okay? Right? Okay. So with this number, now you can change the time delay axis to L by lambda axis. Okay? Right? So velocity into time gives you distance. So you can now plot reflectivity as a function of scale length, second harmonic as a function of scale length, X-ray yield as a function of scale length. Okay. Second thing, now I have to measure, I want to calculate this unknown function of L by lambda. What do? I write down the equation for reflectivity. So I know that when a p-polarized light goes through an inhomogeneous plasma, this is the wave equation it must satisfy. Now this figure clearly shows what do we mean by a p-polarized light. P-polarized light is that light for which the electric field lies in the plane of incidence. And S-polarized light is that light for which the electric field is in the perpendicular plane of incidence. Okay? Right. So you take this wave equation, solve it. You know the conditions inside the solid. So this is your plasma. Light falls from the top, and at the solid layer, you know what the boundary conditions are. You know the plasma, the electric field and the magnetic fields are decaying. You know the magnetic fields, you know its derivatives. Okay? Using those values, you can solve this equation as an initial value problem. Okay? And get the magnetic field and electric field at the boundary of the vacuum plasma interface. Using these values, I think AC is off, right? Okay. So at the surface, you can calculate the magnetic field and its derivatives, and using those, you can calculate the reflectivity. So what do? So now you have a tool. Okay? You can see that this equation has the dielectric constant inside, which in turn depends on nu effective by omega. So you have experimentally measured reflectivity and you have calculated reflectivity. So you tinker the nu effective by omega such that the measured reflectivity matches the calculated reflectivity. If you do that, you get this kind of a figure. The collision frequency or effective collision frequency, because this is not electron-ion collision frequency. Effective collision frequency at the critical layer goes with L by lambda the following way. So if the error bars on this curve correspond to the error bars in the reflectivity curve. Okay, so for each reflectivity value, you solve the wave equation. Change the nu by omega such that the calculated reflectivity and the measured reflectivity match. Okay, if you do that, this is what you get. Now, if you look at the peak value of nu effective by omega, it turns out to be 0.15. If you calculate the electron-ion collision frequency using the standard formula, okay, t to the minus 3/2 multiplied by log lambda density and all that, it turns out to be that this is one order of magnitude lower, which means that the rate at which the wave is losing energy is much higher than the rate which can be explained using electron-ion collision frequency alone. So wave must be damping non-linearly. Okay. So large value of nu effective by omega is a clear indication of damping of the electrostatic wave at the critical layer by nonlinear processes like wave breaking. Now, if you want to model, we said let's model it using a Gaussian. When I did this thing, people laughed at me, but this is what it is. You can see this, I say, this curve is a Gaussian curve. So you fit it with a Gaussian and then use this Gaussian formula into your second harmonic generation formula and X-ray yield formula. And what you get is this, a beautiful explanation. The second harmonic yield perfectly or very well matches the experimental result. And the X-ray yield also shows, except for some ups and downs at the side, it gives a very good matching with the experimental data. So which shows that the excellent fits obtained for both eta and harmonic and X-ray yield clearly shows that the experimental results are in good agreement with the theory of resonance absorption and wave breaking. You can do one more thing. everything. You know L by lambda at 24 picosecond. You know the angle of incidence, and you know this is what you have measured, which is 0.15, which has come out from the experimental data. It turns out that this value is of the order of 1.4. So when I first calculated this parameter, it turned out to be 0.9. Over the years, it has changed from 0.9 to 1.4. But it depends on how I calculate. But it is of the order of 1. So it is 100% sure that the plasma wave at the critical layer is broken. Okay, right. So this is one of the first evidence, clean evidence of plasma wave breaking. So this observed anti-correlation of hard X-ray yield and second harmonic generation exhibits a clean signature of wave breaking. This experimental work represents first one of its kind. I will tell you why it is first one of its kind. Because a similar experiment was done 10 years before also, and it was wrong. Okay, so that's very important. So I'll share those memories there now. So experimental work represents first one of its kind, where the onset of wave breaking has been dynamically timed. So you can see as you change the time between the pre-pulse and the main pulse, the wave grows, and finally breaks. So it is like seeing waves on a seashore. Okay, right. So theoretical and numerical modeling of our experimental results is in good agreement with the theory of resonance absorption wave breaking. So this work has clearly brought out for the first time the link between dynamics of plasma waves, hard X-ray generation, and second harmonic yield. Right. But this is not the end of the story. Okay, there are further puzzles. Okay, first of all, is that why is the nu effective by omega L by lambda curve has a Gaussian shape? Okay, somebody asked me 10 years back, and I told him God knows. Today also I say the same thing, God knows. I do not know why it has the same curve. Okay, so this is something which has come out from the experiment. A theoretical modeling is needed. Second thing, they did further experiments. See, this earlier experiment was done at a fixed intensity, which is 10 to the 16 watts per centimeter square. So when they plotted the second harmonic yield as a function of intensity, okay, as a function of intensity at two temporal delays, one at 5 picosecond and another 21 picosecond, they found that the experimental data deviates from I square scaling. So if its eta is I2 omega divided by R square equal to a number, then the second harmonic yield should go as I square. But what is found is that it deviates from an I square scaling law. So which means that in order to explain this result, you need to calculate nu effective by omega as a function of L by lambda at different intensities. You need further experiments. Okay. So the question is this also an evidence of wave breaking? Now TIFR did some experiments at higher intensities also. Okay. After this work was done, they did experiments at relativistic intensities. They were doing experiments at relativistic intensities. We were doing theory at relativistic intensities, okay, or relativistically intense waves. We showed that if you have a relativistically intense wave, then there is no hard wave breaking limit like a non-relativistic wave. So I'll just write, I'll not describe this work, I'll just comment here that relativistically intense plasma waves in an homogeneous plasma do not have a hard wave breaking limit, whereas non-relativistic waves do have a hard wave breaking limit. When you have V oscillation becomes equal to V phase, the wave breaks. But here the wave breaks just because of relativistic effects. Okay, there is nothing like V os equal to V phase. Okay, and it is shown that because of relativistic effects, the breaking time goes inversely as the amplitude of the wave itself. Cube of the amplitude of the wave. So, and this result is independent of geometry. TIFR has done experiments at 10 to the 18, 10 to the 19 watts per centimeter square, but their data is waiting to be explained. It's now more than 10 years. Okay? So we need more younger people into this group who can look at the data. Theory is all there. Okay? We have done in the last 10, 15 years enough work on relativistic waves, but to explain an experimental data, it's an altogether different ball game.
This data is 10 years old, you say?
Which one? Yes, yes. Even more than that, this data even more than right. I think when Arvinder was doing his PhD, he did this experiment and he gave a CD. I think he gave me a CD. I don't remember now whether he gave it to me or gave it to Ravi. But all this data is there, somewhere there. Okay. But this is at non-relativistic. See, this is at non-relativistic, but they also did experiments at higher intensities. Okay, so now I give further comments. See, there were earlier work done on wave breaking. A very similar work was done by Gizzi's group 10 years back. Before, I mean, this work was published in 2005. 10 years back, 1996, Gizzi's group also did an experiment on measuring hard X-rays and second harmonic emission. They gave some hand waving theory, arguing that the wave is breaking. Okay? But when you go through their argument very carefully, you will see that they are using a resonance absorption theory at a scale length which is smaller than unity, where resonance absorption theory doesn't work. Okay? So this, although it was a PRL, there is something fishy here. Recently, or not recently actually, on relativistic waves, there was one work by Victor Malka's group in 2002, who showed, I mean, they found that the relativistic waves break following Ekhazer-Pelovin formula. Again, we showed in our work that this thing is not correct. Relativistic waves do not have a hard wave breaking limit. So the theory cannot be, their interpretation of experimental result cannot be right. Now, recently, 20 years down the line, the same group has done, you see Victor Malka here and Victor Malka there. Now they have direct observation of relativistic waves. Again, I have not gone through this paper. This is 22 Nature Physics. So one has to see whether they have really seen the breaking of relativistic waves. Because relativistic waves do not break suddenly. They decay slowly through a phase mixing process. They have written this paper, but they have not referred to our work. Very nice. But I see a TIFR connection here because Shiroy Tata is Ravi's student. He went for a PDF there and probably did this work. Okay, now I'll share some memories related to this paper. This paper took a long time to write. In fact, I think around 2 years. When I first gave this, first draft was written and sent to PRL. So after it was submitted to PRL, I knew something dangerous is going to happen because there is already one work, similar work in 1996. So after that, after submission of the paper, we went for a conference. That was in 2004. At that time, I think Professor Kao was chairman of International for a conference. I was with Atre and Singh Saab. We went to IAEA conference. Okay, so that time I had the habit of, carrying all my notes with me. I knew that if the referee replies comes in between, Professor Kao is going to ask me kya hua. Okay, so I was carrying all my notes. It happened that in the airport I lost my bag. So anyway, so one day was fine. I went without shaving, without taking bath. It was a nice day. I don't know what Atre did, but Atre also lost his bag. Okay, so, but after one, flight. In the airport, somehow the bag vanished. Okay, but it came after one day, and surprising, the referee report also came on that same day. Okay, so my notes were there in the bag. We sat down, looked at the reasoning again. Referee had given very tough comments. And in fact, I think it was probably somebody from the Gizzi's group only. Says it's the same experiment, so what are you all doing? It's all, it's not really right. So again, we gave some reply, and during that time, Professor Kao was, visiting Vienna for IAEA office, I think. So one afternoon, he called me. He said, let us discuss again. So, because we had to give a reply, we gave some reply, but it's not satisfactory. You know what PRL did? PRL took our replies and gave it to 2 more referees. So it was 4 referees. and 4 referees attacked us again. So anyway, so he called me, he said, one afternoon, see, आओ मेरे घर में, let us discuss. Okay. So he drew this picture on my notebook. And he was staring at it for a long time. So, you know what is it? This is actually a light wave, airy function of the light wave. And it is exciting a plasma wave in between. So that thing is a plasma wave. So he was wondering that the plasma wave must also follow a airy profile. So that time I think this, if I remember correctly, this idea that the plasma wave wavelength at the critical layer should go as lambda d square L to the power 1/3. This is not discussed generally in books, but there is some work in Ginsberg book which Professor Kao had read. So he said there is Ginsberg mein shayad kahin hai. So anyway, so this was given. So what happened is, after we discussed, while we were discussing, Professor Kao loved sweets. Okay, so when we are discussing, Mrs. Kao brought a plate of Kaju Katli. Okay, so I pick up and I was planning to eat. Professor Kao will ask a question. So, so I leave the thing, again pick up and eat, he'll ask a question. So after, anyway, the questions were not answerable. We were asking, so after some time I said, okay, whatever happens, let's finish the sweets and let's leave. So nothing came out, only some vague ideas that this is the way to answer the referees. So I came out and he went away inside. So I was coming out of his house, and he had this habit of feeding stray dogs. You know, he also had this, I mean, he had a pet dog in his, so जैसे ही मैं निकला गेट से, तो dogs came and they were not allowing me to go out. So I sat there for some time and said, ठीक है, देखते हैं क्या होता है. Professor Kao was inside, door was locked, and I was standing between the gate and the door. So, and that was some summer afternoon. So after some time I said, let me decide. So I rang the bell again. So he came out. I said, you now control them. So what he did, he said, मेरे पीछे आओ. ठीक है? He took me inside. जब तक मैं कार में बैठ नहीं गया, he came with me. Then he said that drive carefully so that you don't run over these dogs or pets. So he was a animal lover, real animal lover. Okay, so this is some memories associated with this paper. And these are my collaborators. The main work was done by Arvinder. What happened was, while we were discussing, since it was taking so much of time, Arvinder had got a PDF at that time, some place in US. I think he got it in Gila. I remember Gila. Colorado. Haan. So he showed me the air ticket. He said, ये ticket है, मैं जा रहा हूँ. So this is the ticket. Anyway, he had gone there. So we used to discuss through phone calls. After 1 year, finally this paper was completed and accepted. Okay, thank you very much. Questions, you can ask questions. Sure.
That absorption curve, it has a minimum of time.
In that absorption curve,
The absorption curve.
reflectivity curve you mean, right?
Absorption where you compare it.
This one? This one?
No, this one, but when you compare it with the absorption curve, I think few slides before.
This one?
This one, and then you look that one, and then you have the right hand side that same curve.
Yeah, yeah.
It's true that it is the minimum is coming at 24%.
It is?
It's true that the minimum of that reflectivity
Hmm.
is coinciding with the maximum absorption. That is true.
Yeah, yeah.
But
No, coinciding, minimum reflectivity means maximum absorption.
yeah, but
This, the left hand side is a theoretical curve.
yes, but then the question is that why the other points, the shape of it, is very different from this absorption curve, because it should happen almost like maximum is fine, but then it is coming down very sharply, whereas it is not coming down very sharply on that side.
This one? You mean here?
No, on that side.
He's saying why is it not symmetric with respect to 24 pixels?
This is not symmetric.
No, symmetric, not symmetric, but not as similar. This fall is very fast from this absorption.
Yeah.
Whereas in your
This absorption is fast. This absorption is also very fast.
no, yeah. So other way, other side, I'm talking.
This is slow.
Yeah.
So this
Why
is slow.
That side slow.
Why is that side slow? Okay, that you mean you want a physical explanation?
Because if you are taking at only the minimum point and you derive from there the whole thing. You have taken that time as
Yeah, I have taken the time. At that time, absorption is maximum. So if I know this time, and I can calculate, since I know the angle of incidence, I can calculate the density scale length.
so if I take another point on that side, because you have both the things
You mean this side?
on that side.
Which side? This side?
No, on that side.
This side?
Yeah.
Huh.
So if I take that point
Yes.
and I do the same calculation,
You cannot, because you have a formula only for the maximum absorption. I know how absorption changes with L by lambda, okay, and I know how to calculate the maximum absorption. So there is a formula for maximum absorption.
but in the last one when you talk about the collision rate, then you have given a with L by lambda. You have given
Yes, that's an input. That collision frequency. See, this theory is for when collision frequency is a constant. Okay. So, but since the wave is breaking, so this theory will not work. So that is why we calculated an unknown function from the experimental result.
The point is that after that wave is broken, that L by R,
Hmm.
any value above that wave is always broken. Is that correct?
It's not in time.
No.
Delay time.
Delay time. This is delay time. So each time delay is experimental shot. So you shoot the pre-pulse. After some time delay, shoot the main pulse. Measure the reflectivity. That's experiment 1. Second stage, again shoot the pre-pulse at some other spot, of course, and shoot the main pulse at other time delay, and plot reflectivity. Wave breaking is happening. Yes. No. and the reflection point increases. But if that increases, the amplitude of the wave which tunnels to the critical point, that decreases. So these two competing effects balance only at a particular angle of incidence for a given scale length. And you can also turn this argument around. For a given angle of incidence, there is a specific value of L by lambda for which the amplitude of the excited wave is maximum. Okay. So which means that the amplitude of the excited wave does not depend only on the angle of incidence or only on the scale length. It's a combination, and that combination is tau. Okay. Huh. Okay. Ekada bolo. Huh? First slide. Acha, first slide. Okay. Huh? This is a polished target. Polished to, I think, lambda by 4, ऐसा कुछ है, as far as I remember. Material is BK7 glass.
No, but I mean, if there is a roughness introduced by mechanical means or any other means, will the result stay?
Yes. That was another paper. So the thing is, so if you have a rough surface, yes, change. Absorption changes, because if you have roughness, then the light wave can excite surface waves. Okay, she was showing. So there are two things. The light falls, heats up the surface expands, right, as a plasma, and it also has corrugations. So there are two things happening. One is the light wave is exciting a bulk plasma wave, and on the surface it is exciting a surface wave. So this surface wave and the bulk plasma wave can interact and enhance absorption. This was another paper in 2008.
I mean, it's a gas or cold? What is the plasma made of?
Glass material.
BK7 glass, silicon, I think.
Glass itself is becoming
Yeah, expanding. Yeah. Glass is. So the intensity is so large, 10 to the 16 watts per centimeter square, that instantaneously it forms a plasma.
But then when you shoot at, I mean, with delta between your pre-pulse and that, then if you do delay, so that plasma would have, say, expanded. Or
Yes, that's the whole point here.
So to what is the rate at which it flows out?
That I calculated. That was the whole thing. See, the week
25
10 to the 5 centimeter.
seconds, huh?
No. The velocity of expansion turned out to be 10 to the 5 centimeter per second. Centimeter per second.
Acoustics we did.
Huh?
Typically acoustic.
Acoustics.
When you delay this by some 25 microseconds, picosecond. right?
24 picosecond. Yes.
So in that, how much would it have come out? I mean, it would
That
expanded.
yeah, that we calculated. See, that number is here.
That's a reduced density compared to short.
Yes. I mean, so there is a density gradient. So light goes and then produces a plasma wave at the critical layer.
So it reaches the glass when you shoot the main pulse, or it
No,
comes off
no. It is getting reflected from the critical from the reflection point, which is before the critical layer. But there is an evanescent field which reaches the critical layer. Therefore, at the reflection point, electric field is not zero. Okay, it reflects and there is a decaying field, and that decaying field is reaching the critical layer, and that is
Critical layer means the glass, or
no, critical layer is where omega is equal to omega
still
p.
further from the glass.
Yeah, still further from the glass. See, glass will have solid density.
Yes.
That's around 10 to the 22, 23 particles per cc. Okay, for this frequency, the critical density is 10 to the 21 particles per cc.
So it will come off before.
So it is before the glass. Yes.
So the second harmonic generation is due to the interaction between the driver and the plasma's own waves.
Yes, 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 yes. Driver नहीं उसमें see okay
The main line plus
the main light electric field plus plasma wave electric field. Both electric fields are oscillating the electron. That oscillation velocity is interacting with the plasma wave density fluctuation itself. So delta n.
What is the reason for second harmonic? I'm trying to understand the harmonics own. Why the second and why not other?
You can have third, fourth harmonic. There are orders of harmonics. You can generate.
Are you able to detect second, you will say, or what?
You can detect higher harmonics also.
You said
I think Kundu has done some work on higher harmonics. Yes.
so it will generate all harmonics.
Yeah.
There are some selection rules.
Yes.
This is the dominant one.
Huh.
I remember there was a paper. There was a paper by Kumar and I think Professor Sood's group on nanopattern surface image laser was
Correct. They have done many experiments on nano patterns. Yes. Yes.
Their results were quite different because you told lambda by 4. There the surface undulations were even lesser than that. I'm trying to take a look.
No. What do you mean by a polished mirror? Polished mirror means the undulation should be of the order of a wavelength or fraction of a wavelength.
So it can be polished even more than that.
Yeah, you can polish it. Better the polish, more the money you pay for polishing.
Polish can be even more than that.
Yes.
Like the surface of a silicon used for semiconductor application. Your undulations are even much lesser than this.
But it's not even reaching.
No, but no, Mukherjee,
It's not reaching.
it depends on which wavelength they are using. Polished for which light wave? Polished for radio wave will be very different from polished for a visible light.
It must be very red or something, right?
This lambda is about
800 nanometers, like
Yeah, point head micron. Yeah, yes.
Almost, I mean,
so 200 nanometers.
boundary between red
800 nanometer.
800 1/4 is 200.
Okay.
And the nanopattern surfaces are less than that, about 20-30 nanometers. But those results are different. It gives more electrons coming out and things like that.
That is which light? Laser light?
Same. If I remember, it is the same. I'm just trying to understand that is it the surface? Does the surface play a role?
Surface plays a role. Surface plays a role.
evaporation it will, right?
नहीं, surface
Making
plays a role. See, देखो मुखर्जी एक चीज है. Surface will play a role when the surface wave dispersion relation is satisfied. The thing is, the K has to be such that it can excite resonantly the surface waves.
Maybe he's talking about you're talking about recent work? Because this is just 1 minute. It's a 20 years ago experiment and the laser power increased recently in his lab. So higher power, the J cross B effects are...
Other effects में काम है. ये क्या higher power पे था?
Power to
This is non-relativistic. This is non-relative.
10-12 years.
This work is 20 years. They have been upgraded.
but पहले का अभी का recent paper से.
So I'm in love with this 20 years old work. So that's what I'm presenting this.
And now they will have petawatt laser.
Now they have a petawatt laser. But the thing is, relativistic wave breaking, something which we must do because there's only one nature physics paper which may as well be wrong on narrow nose. Yes?
What is the mechanism of X-ray generation?
Okay. The X-ray generation is when you have electrons are through Bremsstrahlung generating X-rays. Simple.
It's a Bremsstrahlung or it's a line X-rays? It's a line emission X-rays or it's a Bremsstrahlung X-rays? What is the procedure? Because you have a second harmonic generation, whatever it is. Then how it is generated? Through collisions or what? What is the mechanism of that?
It must be, see what is happening, you have energetic electrons and a fully ionized plasma. Okay, so what will happen when the electron passes close to an ion? It will get deaccelerated.
You have fully ionized.
You have a fully ionized plasma. That's what the gas is. Ion is fully ionized because the laser power is so high that probably all electrons have been stripped off.
So what is then the energy
Okay, so see this X-ray energy is 30 to 300 keV in that range, okay, and the laser energy is 3 millijoule I think, 3 millijoule in 100 film per second, 3 millijoule total.
Laser wavelength, right? Yeah. I'm asking that what is my input energy and means how much I am converting. Input energy, then we will.
Input energy is low, so it is actually drawing energy from the plasma.
But this is the focused intensity. This is the focused intensity, 10 to 16 going at the focus.
Hmm.
So the intensity at the focus is very.
But still, the photon energy, laser photon energy is very low. You can calculate
Sir, means the X-rays are drawing energy from the plasma.
somewhere, yes. Okay,
I think we should close.
we'll close. Thank you.
Today our director was not able to attend this program due to the meeting at DAE, but he has sent his message. I'll read out his message. I was not fortunate to work under the guidance of Professor Kao, or even meet or interacted with him, but I have heard a lot about him, who is the visionary founder of the Institute for Plasma Research and world's one of the most distinguished plasma physicists. Under his leadership, India became the full partner in the ITER project and emerged as an important participant in the global fusion research. He has greatly enriched our understanding of plasma physics and its important applications in many areas for industrial and societal applications. Even though he is no longer with us, his vision continues to illuminate us, and his legacy continues to inspire the generations. I will take this opportunity to thank Professor Sen, Professor Das, Professor Bhatt, Professor Deshpande, and all participants for making this commemoration program a success. I also thank all the online participants, and a special thanks to Madam Kao for joining us. May the memory of Professor Kao continue to guide and inspire us all. And when Sudeep asked me to read this, I thought that I will also take some opportunity to say something. To me, that we remember him not only for his intellectual brilliance or his immense scientific achievements, but also for the inspiration he provided to all of us and also to the future generation. We strongly believe that science should be pursued with complete freedom of thought and implementations. In his retirement speech, Professor Kao in 2013, he mentioned that only sky is the limit and IPR offers opportunity as well as freedom, but assumes that you will work with dedication and responsibility in whatever you choose to do. And you all know that what freedom we have got. I remember that during Kao Memorial, there was one Kao Memorial program in 2017 in EDI, where Professor John mentioned that once he asked Professor Kao, can I do the plasma processing here? He said, yes. You are in IPR, you can do anything you want. So that much. Buddy, you are in IPR, so you can do.
Professor John was talking of some movie where he said this is New York.
Yes, there is New York here. He has shown that figure. So So his true legacy lives in the students he guided, scientists he mentored, the institute he built, and the dream he inspired. In his retirement speech also he has mentioned how his journey began from one room in PRL to this institute at that time, 2003. He said that I see that my colleagues have done me proud by sticking with me through thick and thin, and what we have come a long way. The dream is more robust. The dream is more robust now, but we still have to have a substantial distance to travel. Yes, now we are committed to travel that distance to make your dream true. That's our commitment. So at the last, I just want to thank the organizer, particularly Sudeep, Pintu, Sarveshwar, Mrityunjay, Saroj for his beautiful video presentation, and your team also, and Gaurav, the PSSI secretary, Rahul from Outreach for making this commemoration program a grand success, and we'll be having many more this kind of program. Thank you once again for attending this program.